All right, hello everybody. Welcome to exam 2 prep office hours. This is going to be pretty similar to the first one. It is going to go probably pretty long, just like last time. I did get asked a lot of practice problems this time, so I'm going to kind of like play it by ear and somewhat leave it up to those in attendance. I'm either going to go over a lot of them, but quickly and not answer as many questions, or we might go over some of them and try to go more in depth and answer questions. I guess we'll kind of see like how each question plays out. Um, I, I, I think Dr. Brittle assigned some like 20 plus problems. I just don't think that's like we'll be able to go in detail with all of them. Otherwise, you guys are going to be here until exam time. So um, let's see. Quick disclaimer, your voice or video will be recorded if you decide to speak up. Not generally an issue, but just be aware of that. And then if you're not asking questions, please mute your mic so that we don't have any noise. And again, I won't be sharing these slides. I go into quite a bit of detail on a lot of this, the material in class, and we don't want that to like negatively impact the class by having that shared out in the wild. So feel free to use the recording as you need and take screenshots if you want. So the exam 2 layout is very similar to the exam 1 layout. There's going to be 2 graph design questions and then the set of multiple choice questions, and each of those will be worth 20 points for a total of 60 points. Hopefully this isn't a surprise to anyone. Someone has their mic on. If you could turn it off, please. All right. So to go a quick summary of graph algorithms, you want to treat the algorithm as a black box. This is even one step further than the divide and conquer black boxes. In graphs in our class, we do not allow you to tinker with the black boxes. You're not allowed to modify them. You're not allowed to, make them change the behavior differently than the ones the way we have presented in this class. So it is a pretty substantial penalty if you do that. So make sure you don't do that. All right. You want to consider the inputs of your problem, and then you want to consider what the output of your problem should be, and then what black box you need, or a series of black boxes that you need to sort of chain together. There are times where you might start with one black box, get the output from there, do some modifications to the solution, and then put it into a second black box and get an output. So, yeah. And then the challenge of this topic is to frame your problem as a graph. So you may not get a graph as a initial input to the problem, and you'd have to say, okay, my vertices are going to represent this, and my edges are going to represent this. So always make sure that you start with a graph when you are working on a problem. If you don't have a graph, tell us how you make that graph. Okay, it's very important. And then you want to manipulate that graph so that the black box can solve it. That might mean different things. I'll go over some of the typical ones in a few slides later, but you want to maybe make changes to that graph. Maybe the graph that you get isn't exactly what it needs to be in order to solve your problem. And then selecting the right black box based on your input and output needs. Justify your correctness and runtimes, just like the divide and conquer problems. So make sure you do that correctly. And then this type of problem solving is called a reduction. You take a known black box to you, and you reduce your the problem you're working on such that you can solve it using the black box that you know about. Memorize graph properties. These are very important. What a directed and undirected graph are, unweighted versus weighted graphs are, what a connected component is, which only makes sense in the context of undirected graphs, and then strongly connected components only make sense in the context of a directed graph. Know what sources and sinks are, which is in directed graphs. Undirected graphs do not have sources and sinks because travel on the undirected edge can go, either way. So there's no sense of source and sink. Understand what cycles are, how to detect them, both in a directed and undirected graph. Understand what bridges are. These are specifically in a undirected graph, and understand what leaves are, also in the context of undirected graph. And these are like, these may not have been mentioned in the lectures or in the book. They're sort of you should know what this kind of term is. But I will go over real fast for those who might not. All right. So suppose I have a graph that's like, whatever. And then this right here. Okay. So this right here, this edge is considered a bridge. And what a bridge means is that if I was to delete this edge, I would get one more connected component. It means that bridge is required to keep my connected components connected. So if I was to say, delete this edge, I still have one connected component, and therefore it's not a bridge. And then if I delete this one, it's still a connected component, therefore it's not a bridge. It is only this edge right here that is considered a bridge. And then a leaf node is any node that's at the end of a bridge or connected to only one other vertex, right? So this would right here be considered a leaf. These are good to know for spanning trees. So if you have like a spanning tree of yeah. So if you had that, then this would be a leaf node. That's a leaf node. That's a leaf node. Okay. So those are your 3 leaf nodes on your spanning tree. Okay.
So just to clarify, the leaf node is the node that becomes its own component, or is no longer a strongly connected component when the bridge is removed, right? Like it's not on both ends of the bridge; it's only the one.
Correct. Yeah. So it's just any node that's only connected to one other node. So it's good to know. I would say leaf nodes are really important to understand because they come into play when we talk about MSTs. And a bridge is just what connects to a leaf node. So it's kind of good to like understand what that term is. Okay.
I have a question.
Yep.
Can we have more than one bridge?
Yeah, absolutely. So if we come back to my little drawing here. So like I said, it's any bridge is a bridge is any edge connected to the leaf node. So if I have 3 leaf nodes, right? I have this one's a bridge, that one's a bridge, and then that one's a bridge. This one's actually a bridge too. Oh, I take that back. It's actually not. It's not. So a leaf node is always connected to a bridge. A bridge is not always connected to a leaf node. Right. So like if I was to delete that line, it would. Let me just make sure that I'm right on that. So if that's the case, then I think all deletion increases the graph number of connected points on one. Yeah. So I think a MST, all the edges are actually considered bridges. Yeah. So all edges in a tree are bridges because if you disconnect any of them, then you have effectively added connected components to your graph or created more connected components. Okay. Hope that helps.
Okay. Also, if you remove that bridge, will it still be? Would that vertex still be a leaf node?
That bridge does not lead to a leaf node, right? Because this vertex is connected to 3, and this vertex is connected to 2. So those 2 are not considered leaf nodes.
Okay.
Okay. All right. Let's go back to the slides. Know what a DAG is, directed acyclic graph. They have important properties. Some of the problems that we will be solving today specifically only works if the starting graph is a DAG. Sorry, it's a little hot in my room. Take off my jacket. And okay. So graph solutions, the way that they are addressed in this class is that you need to describe your algorithms in words. Again, this is very similar to your the divide and conquer problems. Don't use pseudocode. Do not modify the black box. This is a big important change, okay, from the previous topic. Do not modify the black box. It is, I believe it is -4. So if you modify your black box, you're immediately going to lose points. Even if it's completely correct, you're going to lose points because you're not allowed to modify the black box. Instead, modify will create the graph input. And then if your problem isn't a graph, make sure to frame it as a graph. So, and then use the black box output to form the solution. So you may not get the proper solution from your black box, and you might have to make it change to your black box. Someone in chat says -4, okay, noted. It starts at a -4. If modifying a black box completely trivializes the problem, it is going to be more than -4. It is at least -4. don't just be like, you know what? If I modify the black box, I get 16 points. I'm okay with that. And if doing that is a super easy solution, it's probably going to be a bigger penalty than that. Okay, so don't just do that just because you think it's only going to be -4. All right. You need to explain why your algorithm is correct. Why did you pick the black box? Why did you make the changes to the input graph? Why does the output help solve your problem? So, the usual things that you need to say in order to present your solution as a correct one. You should analyze the runtime for graph manipulations you made. So, if you deleted a bunch of edges, how long did it take to delete the edges? If you reverse the graph, how long did it take to reverse the graph, so forth. And then the runtime of the black box you ran, just state it. Memorize them, obviously. Don't give the wrong runtime for Dijkstra's or Prim's or Kruskal's. You got to remember those black box runtimes, but then you don't have to prove them or anything. You can just say Dijkstra's is O of n plus n log n, right? Prim's is m log n. I think it's m log n. Yeah. And so just memorize those runtimes. We'll go over runtimes a little bit when we go over problems. So the overall runtime should be in big O, as is the case always in this class. So this is how I like to break the different algorithms in this class. So to me, DFS, Explorer, SCC, topological sort, and the two-set algorithms are all very similar in how they work. They are all based on basically DFS, right? You run DFS multiple times, or you do something with the output with the DFS. There is a specific difference between Explorer and DFS in our class. I believe it is in your graph post that was posted by one of the TAs. Make sure you go read what the difference is. The gist of it is that DFS basically runs Explorer from every vertex, and Explorer runs it only once from one vertex. So if you wanted to know if S is connected to certain vertices, you run Explorer and then check the visitor array. You cannot do that straight with DFS because DFS is going to use the visitor array to track how many times it runs Explorer. So by the time you're finished with DFS, the visitor array is going to be true on every single vertex, no matter what. So that does not really check for the connectivity for you. You have to do extra steps. So I would say use DFS for almost everything. But if you want to know if S is connected to T or U is connected to V, etc., use Explorer. SCC is a super important algorithm. Do not run SCC on an undirected graph. It has no real meaning for an undirected graph. SCC is specifically for directed graphs because we care about the strongly connected components. Undirected graphs do not have strongly connected components. It has connected components. So doing the SCC algorithm in an undirected graph does not make much sense. Topological sort, you can kind of say this in multiple ways. You can say, I get the topological sort of this graph using DFS. I run DFS and get the topological sorted array, or I run the topological sort algorithm and get the topological sort. Like you can state this in various ways, but you should understand that topological sort is just basically a run of DFS, and then it's a sorting, a non-comparison sort of the post order numbers. Yeah. And the fact that it's not a comparison sort, I think we talked about this in the previous office hours. If it's not a comparison sort, it can be done in O of n rather than O of n log n. So topological sort is an O of n. And then the two sat is you should, I don't want to go over it too much, but you should go, watch lectures on how we take a CNF, turn it into a graph, and how we solve that graph and then answer the two sat problem. Okay.
I have a quick question.
Black box. Yep.
On the topological sort, we can use it directly from DFS after we run it. I believe it's part of the output arrays.
Yeah, you can just say run DFS, run the DFS, get the topological sort of the vertices. Oh, and here's something. Here's a tip. If you can't remember whether the post number, how the graph is reversed and stuff like that, and where the if the larger post number is a source or a smaller post number is the source, I always kind of forget. I always have to look it up. Just say that you're sorting it from source to sink. That's all you have to say. Just say that the first vertex is a source and the last vertex is a sink, and you can go from there. You don't have to give like the details of how this sort works. You want to know where the source is. You want to know where the sink is. Say that you run topological sort using DFS, and that the first vertex is a source, and then that's it. Don't worry about the post order number. Do not. I mean, you can, but don't do it because that's a bad idea. Try to give us the details of the SCC algorithm. Like, yes, you could run DFS, reverse it, run DFS again. Most people will make the mistake of like just the right steps. Technically, you're using 2 DFS black boxes, so technically that's allowed because you haven't modified the DFS black boxes, but it's a bad idea. You have the SCC algorithm given to you as a black box. Just use it as is. Don't try to remember the details. It's not worth it. So there's that. Okay. So yeah, know the different black box algorithms. These are all going to be all of n plus m. DFS Explorer works on any graph. SCC only works on directed graphs. Do not give the details, right? That's what costs you points if you make a mistake. Topological sort only matters on DAGs. It only works on DAGs. If it's not a DAG, you can't use topological sort. You can take a graph, a directed graph that's not a DAG, get the SCC, the SCC metagraph, which has to be a DAG, and then use topological sort on it. You can do that, but if the graph itself was not told, you were not told that it's a DAG, then you can't just assume that you can run topological sort on it because it won't work. Yeah, so you usually use on the SCC metagraph to give information about the relationships, and we have problems about that makes use of this. So I'll show that in a little bit. First SCC is a sort, last SCC is a sink, but may not be the only ones. This is super, super important. You don't know how many sources, like without additional work, how many sources a graph, SCC sources a graph might have, or how many sinks. You cannot just assume that there's one of each. You can't assume there's more than one of each. All you're guaranteed is that the first one is a source and the last one is a sink. Some people will ask, do all graphs, all SCC, all directed graphs have a source and a sink SCC? And the answer is yes. You could have a single strongly connected component, whereas all vertices can reach all other vertices. In that case, you have a single SCC. That single SCC is both a source and a sink, okay? Because sources are defined as having no incoming edges. Sinks are defined as having no outgoing edges. If you have a single SCC that has no incoming edges and no outgoing edges, it is both your only source and your only sink. Okay? So try to keep that in mind. Someone has their hands up?
Hi. So what is a non-comparison sort?
So non-comparison sort, I went over this when we did Divide and Conquer. divide and conquer, like a merge sort or quick sort or most others, most sorts that you have learned, has to compare the actual elements that you're sorting. So like is A greater than B, is B greater than C, so forth. Like those are called comparison sorts. A non-comparison sort means that given knowledge about what you're sorting, it might not matter how one compares to the other. It just might matter about what the item is itself. So something like a radix sort or a bucket sort or a counting sort, where you're saying, okay, if this is a 1, put it in this bucket. If this is a 2, put it in this bucket. You don't have to compare the two things. And so then the runtime is how many items are you putting into buckets. And topological sort, you don't actually compare the post order numbers to each other. You know that they're distinct. You know that they run from 1 to 2n. And so you can just start sorting them by putting them into the right spot without actually comparing them. So topological sort is considered a non-comparison sort. Okay? All right, let's move on. Oops. All right. Yep, don't need to provide details on finding the first force and the first sink. Just state it. You do need to provide details on finding other sources and other sinks. So if you are seeing if your graph has multiple sources or multiple sinks, you have to think through that and put down the details on how that is done. 2SAT lets you solve Boolean satisfiability problems, while other problems involve reducing to a graph. 2SAT involves reducing to a 2SAT CNF. Okay, so you are not trying to create a graph with a 2SAT problem. You're just trying to create a 2SAT CNF. Okay. So some strategies that you can use on these type of problems is that you can remove an edge or certain edges and then run explore DFS to determine what happens without the edges. So consider what would happen if you remove an edge that's special, that's specially called out in the problem. What happens if I remove it and then run DFS? What if I remove it and then run explore? Maybe something interesting can come out of that. And we'll see that going for in some of the sample problems. Do a graph reversal on directed graphs and then run explore DFS. Like so one key trick. Actually, maybe I can just try here. Turn on pen. Okay. So one key trick is that if I have, a vertex that's coming here and a vertex that's coming here, right? And my question is, which vertices can reach this vertex right here? Okay. Well, the really, the slow way would be to, okay, well, if I run explore from here, I'll know which vertices this can reach, and I'll know if it reaches here or not. If I run explore from here as well, I can also find out if it reaches this vertex. So that's 2 runs of explore, and then if you do it for over every vertex, you end up with a n times n plus m, right? So that's actually not very fast. What you can do instead is that if you took this graph and you reversed it, and you reverse the edges, and then I can't delete. Can I delete? Nope. Okay. Oh no. All right. Try this again. All right. And then if I reverse this, I get this little graph here. So if you first reverse it and then you run explore from this vertex, whatever the vertex can reach in the reverse graph is equivalent to whatever vertices can reach it in the original graph. Okay, so whether doing a graph reversal and doing that is super helpful on certain problems. And I think we have a sample problem that'll do that. Okay. If you are doing a graph reversal, you can just say I reverse the graph. You don't have to give the details on how a graph is reversed. On top of that, but you do need to know the runtime, and it's all n plus m to reverse a graph. Okay. Other tricks you can do: get SDCs and use it to get more information about your graph. This is generally when you're trying to solve a connectivity problem. like, if A can reach, all these vertices, it's considered a special vertex. Can it reach all these special other vertices? So SECs is really good for that because it compresses your graph into a meta graph that you can work with, especially being able to topologically sort the SEC metagraph is super important. You can't topologically sort a directed graph unless it's a DAG, and so you can't do it on the original graph sometimes, but you can do it on the SEC metagraph if you get the SEC, run the SEC algorithm. Get SECs and use it to determine pathing, connectivity, cycles, etc. So I just said that. If you've given it DAG, you could possibly sort it and go down the ordering and look for information. So that's something to consider. And then you can finally for 2SAT, the strategy is to encode your problem into a 2SAT CNF, run the 2SAT algorithm to determine the answer that you're looking for. Okay. And then if you are running Explore or DFS from every single vertex, you're probably this with, well, DFS runs Explore from every vertex, and that's not true. DFS runs Explore from every unvisited vertex, right? So once it goes through all the vertices, once it goes through one path to get all the vertices that it can visit, it eliminates a lot of the graph to continue running Explore from. But if you go and run Explore, like I said on this problem, like if I run Explore from this vertex, then I run Explore from this vertex to try to get information, that's going to be slow versus reversing it and running Explore from a single vertex. So don't run Explore or any of these algorithms from every vertex. And that's the case for just about every single algorithm on this topic. Don't run a algorithm, algorithm that's going to explore the whole graph from every vertex. That's almost certainly a bad idea. Okay. BFS and Dijkstra's. So these are shortest path finding algorithms. Okay. You need to know the different black box algorithms. Find the shortest path. Finds the shortest path for graphs. BFS tells us how many edges from S it takes to reach all other vertices. It does not consider edge weights. If you run BFS on a graph that has edge weights, it will not determine the shortest path based on the edge weights. It only determines how many edges it takes from the smallest number of edges it takes from S to all other vertices. It needs a source vertex, right? Because it needs to know the distance from a single source. It is a O of n plus m algorithm, and then it can also see if S can reach a vertex. Okay, so any vertex that S cannot reach gets an infinite distance. Okay, Dijkstra's does consider edge weights, needs the source vertex as well. It's all n plus m log n. Can also see if S can reach vertex V, infinite distance if it can. It does not work with negative weights. This is not a trick. It does not work with negative weights, regardless of whether there's a negative cycle or not. Dijkstra's is a greedy algorithm. The assumption that Dijkstra's makes is that with every single step away from the vertex, a distance can only increase. Okay, so if it thinks it's found the shortest path, it's not going to consider another edge. It cannot consider that taking an edge can actually decrease the distance. So even if there's no negative cycle, Dijkstra's does not work correctly. Okay, so never ever run Dijkstra's on a graph with negative weights. Let's see what else.
I guess just thinking about that, is there any manipulation that can be done to a graph to convert those negative weights to positives and then have a meaningful connection back to the original graph?
We actually have a problem. That's a practice problem. So we'll go over what that looks like.
Looking forward to it. Thank you.
Okay. So yeah, those are the two. Okay, so the strategies that you can employ with these two algorithms, very similarly, remove an edge. If an edge is being called out to be special, what happens if you remove it before running DFS or Dijkstra's? Does it do something special for you? Also do graph reversals. So similarly, how I said with explore, you can check for connectivity. If I had a question like, oops. Right. If I wanted to know the shortest path of all vertices to this vertex right here, I do not run dice rows from this vertex and dice rows from this vertex and all the different vertices, right? What I'm going to do is I am going to reverse it and run dice rows from just this vertex right here. Because the shortest path from all vertices to a single vertex is the same as the shortest distance from that vertex to all other vertices on the reverse graph. You don't have to prove this. This is a known property of graphs. Okay, so if you wanted to know what is the shortest, what vertex is closest to my target vertex, you can just reverse the graph and run dice rows from that target vertex as if it's a source, and it'll be the same distance. Okay. So do that. Run dice rows multiple times to get information about a graph from different sources, generally twice. So I think there's a problem that will show this, but if you're running dice rows like once or twice or some constant number of times, that's okay. You can say that's still the same runtime as dice rows. And you will see how we manipulate the graphs to do this. So this is an interesting approach. But do not run dice rows from every single vertex. That becomes a really slow runtime. Okay. Running BFS and dice rows from every vertex is a really bad idea, just like any other algorithm. Okay. Any questions about BFS and dice rows before we move to Kruskals and Prims?
Yeah, I have one question.
Okay.
So going back to the BFS and Dijkstra, is it okay to say, because if you have a BFS and then you run Dijkstra on a graph where all the edge weights are 1, the results will be the same, right? BFS and Dijkstra will give you the shortest path in that graph.
It'll be slower. You don't want to do that. It'll be slower. So if you look at BFS, it's all of n plus m, right? For Dijkstra, it's all of n plus m log n. Like Dijkstra isn't going to know that all your edge weights are 1, so it's going to run through all of it, and it will be a slower algorithm overall.
Okay, got it. Thank you.
Oh yeah, cool trick. If you want to spell Dijkstra and you can't remember, so it starts with a D, and straws is easy, and this right here is IJK. So D, IJK, straws, Dijkstra. That's how I remember it. That's how you should too. I mean, if you misspell it, it's obviously you're writing Dijkstra. You'll be okay. But sometimes I read a student submission and they've spelled Dijkstra like 7 different times on the same one because they just have no idea. It's pretty funny to me.
When we reverse when we reverse the graph for running like Dijkstra, do we have to negate the edge weights?
No, you can. Reversing the graph just means taking all the edges and pointing them in the opposite direction. The negating the edge weights is called inverting. Inverting the graph. Reversing the graph is reversing the edges. Inverting the graph is inverting the edge weights. Okay. And you don't want to do that with Dijkstra because it doesn't work. We'll show you why it doesn't work in one of the practice problems, but that does not work. All right. Kruskals and Prims are MST algorithms. Know the difference between the two black boxes. You should understand how both of them work, but I tend to say that if you are just running either to get a MST, go with Prims because it's easier to spell. But you can use either. But there are differences between the two that you should understand. So know what the cut property is. Know what the cycle property is. If you don't know what these are, look them up. The cut property and cycle property should both be in your book. If not, look up Wikipedia. They give a good explanation. The cut property means that, if I have a bunch of vertices here and a bunch of vertices here, and even before anything's connected, if I put a cut between, if I put one subset on one side and one subset on the other, the lightest edge across this cut is part of some MST, not part of all MSTs, but you can create an MST with the lightest edge. And if there's multiple of them, they're all in some MST, okay? And then the cycle property just says that if I have a cycle like so, and this is 1, 2, 3, and these can actually it doesn't actually have to be unique. It means that this one cannot be part of the MST. The heaviest edge of a cycle can never be part of an MST. Okay, so this would not, like, you just know that this is not part of MST. Right, that's the cut property. Okay, defines it MST for an undirected connected graph. When you are told to find the MST of a graph, unless we tell you the graph has special properties, when you are told to find an MST for a graph, you can assume that that graph is connected, and you can assume that graph has an MST. We're not going to be like, okay, well, you didn't do all the special steps to make sure that the graph is actually connected. You can assume that you can get an MST. But there are some MST problems. They'll be like, oh, this graph is missing, is not fully connected, and we want to do something to get an MST. So like, you can't make that assumption there because you're explicitly told. But if you're not told anything about the graph and you're told to find an MST, you can assume the graph is connected. An MST only works for undirected graphs. It does not work for directed graphs. Yeah. Both of these runtimes are O(m) log n. That's how long it takes to find a MST. Kruskal's sorts the edges by weight, and then grab the lightest edge that will not create a cycle when added to the MST. So that's how Kruskal's work. Another way to look at this is to never add edges if both endpoints are already merged, and look up union find. That's in the book, in the lectures on how that's sort of determined. If you don't know what union find is, another term for this is called the disjoint set. It's a very cool data structure. Has uses outside of Kruskal's, so it's a good one to learn. But that's how how Kruskal's runs. It uses this union find data structure. Okay. Keep doing this until all edges that will not create a cycle are added. And then another way to look at this is that if all your nodes are connected, then you are done. You don't have to continue. Like if all your vertices, like if you have 10 vertices and they're all connected and there's like 30 more edges to look through, you don't have to consider them because all the lightest edges are considered first. So all the edges after that will be heavier and they won't be part of the MST. Okay. Prim's algorithm is a little bit different. You start with an arbitrary vertex V and you put it into a subtree S of included vertices. Then in each iteration, you grow S by adding the lightest edge between the vertex in S and a vertex outside of S. And then you continue until all vertices are in S. Okay, so I do want to say that even though as a black box, you can run Kruskal's and Prims interchangeably and you'll get an MST, you should really understand what Kruskal's does at each step and what Prims does at each step. Because what can happen on a problem is that you are given a partial MST, and depending on the properties of that partial MST, you may want to continue on the later steps of Kruskal's. You might want to say, okay, well, I'm going to find the next lightest edge and add it to my partial MST. Or you might say, oh, I want to find the vertex that's closest to this subtree I have and add it to my MST. Understanding how these two algorithms work can help you use some of these sub-steps if you're given a partial MST. So don't just ignore what the two are because they're both doing the same thing as a black box. Okay. Strategies when it comes to Kruskal's and Prims. Remove an edge or certain edges and then run Kruskal's or Prims to determine what happens without the edge. Again, this is, you'll see that this is sort of a universal step. You have a graph, you have a special edge, do something with that special edge. Try running an algorithm without it. Try running an algorithm with it doing something else. And that's how you sort of like solve the problem. Make changes to the weights to avoid some edges from being picked first. Now, With MSTs, you can mess with the edge weights, either turning them negative or positive, or adding or subtracting from them, and they do work. They will keep their relative weightness from each other, right? So if I had a graph and I added 100 to every weight, the edges that come back as an MST will be the same as the original graph, okay? Because it does not change where they are when you're sorted. Think about that. Think about you're sorting a number 1 through 100, and you add 100 to all those numbers. Each of those numbers, the original numbers, will still be in the same place when you sort them. So it's the sort of skulls and prims that you have to worry about in terms of their placement on the MST, and so their placement in the sort. So just keep that in mind, and you can do manipulations like that. Okay. Okay. Flipping the sign does not will not. So the question says, I see how constant offsets will result in the same MST. Good, but not necessarily flipping the sign, and that's correct. Flipping the signs of a graph before running skulls and prims does something else. We have a sample problem that will show what that does, but it is not going to keep the same sorting. Okay. Make changes to the weights to force some edges into being picked first. I believe one of the problems, or like, you're looking for a minimum tree such that these following vertices are picked first. You can do stuff by letting skulls and prims pick the edges, but you have introduced priority to some edges, or reduce their priority by messing with the edge weights, and we'll take a look at that. Okay. Be very careful when changing weights. Make sure you think it through. There is a difference between being picked last and not being picked at all. If I tell you that you should not pick an edge for an MST, changing that edge to negative infinity, to infinity, does not prevent it from being picked, because what happens is, if that edge is the only edge left, even with a weight of infinity, it can get picked. You may just have to remove that edge completely so that it's not considered for an MST. So there's a big difference between these two. Make sure you understand that. You can also try running across skulls or prims on a subset of G, and then build the partial to borrow the partial MST, and then add to that MST based on what you're trying to do. Make sure you know that you can use the known MST properties, the cut property, the cycle property, and -1 property to justify your correctness. So if you are saying, oh, it picks this edge because of the cut property, or it avoids this edge because of the cycle property, you don't have to prove these. You just have to know them. Just by stating the cut property allows you to sort of like assert that an edge was picked because of it. Just stating the cycle property, you can assert why an edge was avoided because of it. You don't have to further prove these two properties. These are known properties of MSTs. Okay. Running skulls or prims with each edge removal update is a bad idea. So don't run these two algorithms over and over again, just like everything else. The other thing is that if you're given a problem and it's like this graph is an MST, except for this one edge. How do you find that last edge to the MST? You are going to want to do it faster than doing running skulls and prims from scratch. Okay, that's generally not the solution that we're looking for, and it comes with a massive penalty. Okay, if you just say, oh, I don't have to do anything, I just rerun skulls, like that is not a meaningful solution. It's not a meaningful question for us to ask. Like if your solution to a problem is one sentence, you're probably thinking too shallow of what that problem is trying to ask you, and you shouldn't do it. Okay, so don't just be like, oh, I just run calls and that's it. That's almost certainly not the answer. Okay. Yeah, if you start with an FC and there's change to one of the edges, running skulls or prims to build an FC from scratch is a very bad idea. I actually think this is going to be more than -8. I think this is just like you didn't even bother really trying to solve it, and I think it's like a massive penalty. You might as well have just not bothered. So don't do this. That's a bad idea. All right. How do we solve it then? I think we should have a problem that's a example. Okay. For Fulkerson and Edmonds Karp, know the difference between the two black boxes. Know that max flow equals min ST cut theorem. So this is a very important theorem for max flow problems. So understand what that is. These algorithms gets a max flow for a flow network. For Fulkerson is O of MC, where C is the capacity of the max flow once it's found. This assumes integer capacities. Okay, if you're asked, can for Fulkerson work when the capacities aren't integers? The answer is going to be no. This has to assume integer capacities because of the way for Fulkerson works. If you're interested, there's papers about this, there's Wikipedia articles about this, but the basic idea is that if the numbers are irrational, it'll constantly flip back and forth between what it thinks is the max flow and what it thinks can be a better max flow, and it will actually never terminate. For Fulkerson will go on a endless loop of trying to find a better solution if the capacities aren't rational. So don't run it on non-integer capacities. Okay, so one of the things that's actually interesting about for Fulkerson and Edmonds Karp is that people assume that for Fulkerson uses BFS and Edmonds Karp uses BFS. How this paper was actually written is that the for Fulkerson algorithm is actually a framework of how to find max flow. It says, do these steps, find a path, and then continue doing these steps. It doesn't actually specify what that path finding algorithm is. People assume it's DFS, but it could be any other path finding algorithm. And in fact, there are algorithms that runs faster than for Fulkerson or Edmonds Karp by using a different path finding algorithm altogether. So for Fulkerson never actually specifies it, but it assumes DFS. Edmond Karp is O of NM squared. It works with non-integer capacities. It specifies the pathfinding uses BFS, and because it uses BFS, it can get you a runtime based on the vertices and the edge count. Whereas because for Fulkerson does not specify the pathfinding how it's being found, it ends up being pseudo polynomial and dependent on the capacity of the max flow. So those are the two differences. Understand the two differences. Understand that Edmond Karp is just for Fulkerson with BFS. Understand that one works with integer capacities, one works with any capacity, and the difference between these two. Okay.
I guess in the exam, oh, sorry, you go first.
It's about the previous slide. So you said we can add weights to the minimum spanning tree, but it doesn't necessarily work when you negate them. What do you mean by that? Shouldn't it be the same?
I'll have practice problems about crisscross and prems, and I will specify what happens when we change the weight and why it matters. But basically, if I had pretend these are edge weights 3, 4, right, and these are special edge weights. If I add 100 to these, right, it doesn't change their ordering. They're still going to be in that same order, right? But if I change the sign, they're suddenly reversed on how they're sorted, right? This is now the lightest. This is now the heaviest. So changing the edge weights reverses the sorting. Adding to the edge weight keep the same sorting. So it's important to understand these two. Okay. Okay.
And then I had a quick question about forward focus and Edmund Carp type of problems. Should we expect whether or not the capacities are integer or non-integer to be specified within the exam, or should we assume worst case non-integer capacities for a given problem?
You should only assume the details of the problem given to you. So if I tell you here is a max flow network and I don't specify integer capacity or not, then you should not assume that it'll be integer. If I tell you that it has integer capacity, then you can take that as explicit.
Heard. Thank you.
Okay. All right.
Capacity in the max flow problem is always positive, right? Can it be 0 or negative? It have to be positive, yeah?
Yeah, it has to be positive. I mean, it can be 0. I mean, 0 doesn't like mess up the algorithm, I don't think. Negative capacities would. That additional details, you can assume that that graph is in the correct configuration to be solved with an MST algorithm or a max flow algorithm. But there are was it one of your homework problems? So there was a problem where it's like that for Dijkstra's, and you're just like, assume that one of the edges is negative, but only one edge is negative. Can you do something and still run Dijkstra's or something like that? Like that isn't breaking any rules, but you have to go and fix that problem in such a way, right? So unless you're given details on that type of like special characteristics of the graph, you can assume that if I give you a max flow problem, that it can be solved with a max flow algorithm. And so in order for that to happen, the edge weights, the flow has to be positive, or the capacity has to be positive.
Thank you.
All right. Cool. All right. All right. So for focusing in MX top strategies, there are certain types of graph problems called bipartite that you can turn into a graph problem using into a flow network. Now, some students will ask, is a bipartite graph within the scope of an exam or homework? And I would say that you don't have to focus on a bipartite graph topic, but if I presented you a graph that can be solved with max flow, one of which is a bipartite graph, and I give you the details of this graph, whether you know what a bipartite graph or not before the actual problem is presented to you doesn't really matter, right? You can't say that it's unfair that there was a bipartite problem, even though it wasn't a covered topic, if it means that max flow can just solve it by just knowing what that graph means. So that's like sort of like the scope of like what you have to understand. Like we're not going to tell you what every single graph before a problem is presented to you can look like, right? You should understand how these algorithms can solve certain problems. All right. So I guess my memory was that it was a previous exam problem. Well, don't discuss the solution to a previous exam problem, obviously. But yeah, so don't because you're not supposed to like take knowledge from a previous class and share it with this class, because then that makes it really difficult for us to like reuse problems or reuse any sort of topics. So don't do that. All right, moving on. One such way to solve these type of problems, the strategy is to update capacities to fit the problem. So you might be able to change capacities. And that actually is what happens mostly in these type of problems, where it's like, you have a So that's what you have to kind of think through on how to solve this problem. Add nodes or edges to divert or add flow. I want to say this is in your lectures. I think two of the things that Dr. Bagoda shows I don't remember what those problems are, but that's a approach you can take. You can also add more capacity from S because S has infinite capacity. So when you have a source that's coming out to like, these, this has 2, this is 5, whatever, but the flow coming in here is infinite. So if I change this to 3, I can give 3 and 5 flow fine because the flow coming out of S can be infinite. So don't be like, oh, well, it only has 2 and 5. I can't update this. That's not true. S has infinite flow. You can add more constraints. I can say that stuff like, instead of just 3, I also have a lower bound of 1. So the flow between on this edge must be between 1 and 3. And I think that's one of the type of practice problems that you might see. Find a max flow, then create a residual network and work as if it has a graph using Explore, DFS, or BFS. So you can from any flow that you're given, you can say build a residual network, and building the residual network is considered a black box in this class. Okay, so you do not have to go into details of how this happens. You can create a residual network, and then from the residual network, you can run additional black box algorithms to make sense of it. So one of the steps is like, once you have a residual network in the middle of one of these algorithms, you run a pathfinding algorithm to determine if you have more flow. So what happens if you already have a max flow and you want to increase the capacity of one of the edges? Well, get the residual network, increase the capacity of one of the edges, and see if there's an additional path. If there's an additional path, then you have additional flow that you can add to it. If there's no additional path, then adding that one additional capacity doesn't do anything, right? So that's one approach to take.
The
sample problems.
residual.
I will
Sorry.
be sharing. Yep.
Sorry, I have a follow-up question on the
Okay, I'm
previous
going to
slide.
answer the chat real quick. Yes, I will be going over some max flow problems. What's the question?
For the residual network, if we use it as a black box, the runtime is O of M, as M for edges?
I think so.
That's one of the
check.
That's one of the steps inside the fault focusing, right?
Yeah, let me just make sure that's true. So the creation of a residual graph is actually O of n plus n, because so it's actually what ends up happening is that when you create a residual, so your starting graph, right, is going to have although if you're not, let me think. Yeah, you can go with O of m for creating a residual network. That's fine, because unless like the graph is really weird, it just like an MST problem, a max flow network, a float network is going to be connected, right? Like having some random like vertex over here, some edge over there that's not connected to S isn't going to do anything. Like it makes no sense to have that over there. So you're going to have a connect, like, right? Like this is nonsensical. So you're going to have a connected graph, and in a connected graph, m is greater than or equal to n minus 1. So at that point, m dominates n, and you can say O of m, and that's fine. So yeah, creating this should be O of m because m is greater than or equal to n minus 1. Okay. Someone else had a question?
Yeah, I have a question. So in your example, you mentioned that we have infinite amount of flow that we can use from S, but aren't we still bound by the limit on the edge that is coming from S to the other vertices?
So yeah, so if you, like I said, if you have 2, right, and then you have 5, right, on these. Why does Control Z not work on this? That makes me sad. All right, whatever. That's A. I'm sorry I have such ugly handwriting. I was making fun of Emily in our chat the other day because Emily was doing office hours and she's like, "Oh, I'm sorry, I have ugly handwriting," and her handwriting is actually like perfectly normal or perfectly good. And it's like, that is like a disservice to us who actually have ugly handwriting, right? Like I have ugly handwriting, and then she calls her handwriting ugly. What the heck is wrong with my handwriting then? It's like, worse than ugly, I guess. But anyways, so what I mean is that you can, if you know nothing else about like what comes after this, right? If I increase this to like 100, S having unlimited flow out of it means that it could in fact fill up this capacity if it can, like at some point you have a source and that source has infinite capacity, infinite like outward flow. Does that make sense?
Yeah, that makes sense. The only thing is that there is still a limit from S to A, right? That has a certain
there's a limit from
capacity.
SA, but there's no limit. Like if I kept increasing the capacity of those edges, I could keep filling that capacity from S. Like S isn't like 100. Like it doesn't start at 5, right? It just will keep overflowing as long as you give it more capacity on the edges. I guess it's like a weird way to think about it. Like if it makes sense to you, don't worry about how I just worded it. Like as long as you understand that if I increase the capacity of the edges coming out of S, that I could fulfill that capacity if it's there, then that's good enough. If you understand that, that's good enough.
Yeah, got it. Thank you.
Cool. Another question?
What is the special relationship between a bipartite graph and a flow network? From bullet point 1.
Do I have a problem? One second. Okay. All right. Real quick. Oops. So a bipartite graph to start, right, is a graph that you have a bunch of vertices on this side and a bunch of vertices on this side, right? Such that there's no edges on the same side. So there's no edges between A, B, C, and D, and no edges between E, F, G, and H. So you could have like multiple edges, right? Like this. But there's no edges. Yeah. And so one such problem that you might think you can use a bar chart graph / max flow is like if you wanted to do a matching problem, right? So like if I can only match how do I do this? Let me think. Yeah, so like if I wanted to like match a 1-to-1, so I could set all these edges to 1, and then I can create a source such that I only have 1 to all these edges, and then I have a target such that these are also 1, right? Now, by turning this to the max flow problem, S can only send 1 to each of these vertices, and then each of these vertices can only take 1 capacity. So if I wanted some matching, my optimal answer, if I did have a perfect match, would be 4, right? I could send 4 capacity out, and I can receive 4 capacity such that I get 4 matches. So even if though A has 2 possible matches, I'm gonna try to find 1 match. I'm gonna try to find 1 match for each of these. So one possible match might be A to E, B to H, C to F, and D to G, and that would be a correct matching of a bipartite graph. So this is the kind of thing that you could consider using a max flow algorithm for. But my point wasn't that like you have to memorize what a bipartite graph is, or that bipartite is covered in the lectures. What I meant is, if I explain to you what a bipartite graph is, there's a way to use max flow algorithms to solve it, then it's considered fair, even if bipartite itself wasn't a covered topic. I don't know if we have a practice problem like this, but yeah, that's basically
3.7.
something.
3.7 talk about 3.7 talk about bipartite.
3.7. All right. Do I have a 3.7?
6.7, right?
6.7. Do I have 6.7 as a problem? I don't think I do. Maybe we'll get to it. We'll see. Let's see. All right. I'm going to move on. Okay. Okay. Common mistakes. So homework 5 is still being graded, but I took an early look at some of the common mistakes that students are making. What's interesting about this homework is that there weren't a lot of mistakes that everybody was making. Most of these were like around the 5% mark. So modifying the black box algorithm is around 5%. Try not to do that. Well, don't do that at all. Actually, that's going to lose points. Checks for a fork in the path, but does so incorrectly. I don't actually remember what the problem is. You don't have to tell me. I can assume. But if you're going to do something, like if you state that you have a step, try to be a little bit careful about how you do it. You have to give enough details that if I didn't really know how to find a fork in the path, that you explaining it would make it clear to me. Like oftentimes I think students spend all their time focusing on what that black box that they need is, and not enough time on like the additional steps to do with the output of the black box or the input of the black box. So just don't lose track of that. Correct this justification. To not explain why the graph can be topologically sorted. So you ran an algorithm, or you depended on some property of the graph. You have to explain why that property exists for you to use that algorithm or use that property. So you can't just say I topologically sorted the graph without saying, well, it's a DAG. I can topologically sort DAGs. Runtime analysis. So a bunch of students put down their runtimes as O of V plus E, or O of V, some runtime based on V and E instead of the magnitude of V and E, like O of V plus E. Like that doesn't actually make any sense because V and E are subsets, they're not numbers. So this doesn't come out to be a number. What you mean is O of V plus O of E. And in fact, I actually say you should avoid this altogether. I hate this notation and it's confusing and you oftentimes miss it. Just use N and M. N is the number of vertices or nodes. My handwriting is generally better than this, but I am writing with a mouse. And M equals edges. And this is understood. You don't have to declare what these are. So I just find this notation to be much faster and much easier to remember. And the other thing is that it's a good habit because when you get into the next section, which is NP completeness, N and M also has meaning in terms of literals and clauses in a CNF, and converting from a graph to a CNF actually kind of just works out. So this is the notation I would suggest. You're going to make a mistake on this one. Okay. You do not need to specify the meaning of n and m for TwoSat because, like I said, n is the number of literals, m is the number part of the exam. Dynamic programming is not part of the exam, but Bellman-Ford and Floyd-Warshall are allowed black boxes for a problem. So if you choose to, you can use it. So a couple of things. I'm not going to cover it too much today because those were covered in dynamic programming. And two, those two tend to have rather slow runtimes. So unless you absolutely need to know the shortest distances between all pairs of vertices, I would avoid Floyd-Warshall. And unless you have an unknown number of negative edge weights that could create a negative cycle, I would also avoid Bellman-Ford. But they are there if you want to use them. They're just typically slower than, say, Dijkstra's or BFS or DFS. Or I guess since they're shortest path, they are going to be slower than Dijkstra's and BFS. So unless you absolutely need all the pairs, then don't use them. Okay. All right. So this is the part where we are going to demonstration of our solving. So I have a lot. I basically took the list that a student put, which was Dr. Brittle's practice problems, and I added them here. I don't think we should go over them. Some of them aren't that interesting. Some of them are repetitive over other problems. So we'll just kind of go by our feel. I did write them all down in case there was one that students are like, oh, I absolutely need to know how this one is solved. What I did do at the very least is filter out all the step through this algorithm questions. I think for all of those, you really should do it yourself with your study group or even in ed. Just be like, this is my solution to 3-1. Watching me do it is not going to be very beneficial to you. Like, I think that would actually take away your efforts from you running through these algorithms. So I definitely think they're important. I just don't think it's important for me to cover it. So these are all the problems in chapter 3, all the problems in chapter 4, chapter 5, and chapter 7. So we'll start with 3, and I'll get through what we can, and then kind of depending on how many questions students asked in while I go over them. I'll do more or less. Okay. 3.7 is a bipartite graph. Look at that. So we'll take a look at that. I'm going to take a 5-minute break. It's 3:15. Well, 2:15. We'll come back at 2:20. So use the restroom, go get drinks, what have you. I'll be right back.
Hey, sorry, really quick before you leave, can you go to the next slide?
Yeah. All right.
Thanks.
I'm back, but I'm not going to start for another 3 minutes. How has the video quality been for this office hour? Is it better than the previous one? I recently redid the networking in my house, and I'm hoping that it helped improve some.
The screen sharing is fine.
Okay.
The slideshows look fine, but the video quality doesn't really matter, I guess.
Oh man. Okay.
It's actually been a little bit weird, at least on my end. You're completely frozen right now. And then also what I noticed was that when you were doing those sketches for the flow and the bipartite graph, like the actual like writing was like kind of coming in chunks. And it was maybe about like 3 to 5 seconds delayed from like what you're actually talking about. So I don't know. I mean, that could also just be like teams doing teams things too, because it's teams.
Okay. But some people are saying it is smooth for them. Some people are saying it's not great. Okay.
I mean, for
right.
what it's worth, like I can hear you perfectly fine. Everything's cutting through. So like I think that's good.
Okay. Cool. Whoever was just talking, sorry if I didn't catch your name. Your voice is actually very similar to a coworker of mine. So every time you talk, I was just like, is he in this room? Like, it's kind of fun to me.
Well, I'm very unemployed right now, so I'm definitely not him.
All right. 1 more minute. Uh, 3.5. Okay.
I have a quick question. I guess would it be okay for me to share my notes of the slides after the session on Ed?
Yeah, I think that's okay. Yeah. I mean, look, if it was up to me, right? Like if I had full control, I would share as much material as I can. But the sad part of it is that there are students who are not quite honest, and it hurts the integrity of the class. There have been things that we've had to taken away, and then precautions that we've had to take. So basically, we do what we can, you do what you can, and the more things go out of hand, the more things we have to take away. So hopefully, students understand that and try not to hurt their future peers. That's
and I didn't want to go against the I guess spirit of the course by sharing those notes.
Yeah. No, I don't. I think like 99.9% of students have no are doing it out of the goodness of their heart, which is great, and we want to encourage it. But we're not trying to make life harder for you. It's at some point, there are some limits we have to set. Otherwise, this class would just, everybody would just share everything, copy everything, and then nobody learns anything, and that's not good for the class or the program. All right, we are going to start with 3.5. Right. I hope, yeah, 3.5. Okay, so I'm going to paste this because it's actually very, very trivial. And again, you don't actually have to know, I mean, you should know, but you don't actually have to ever write this down anywhere. Just kind of understand how it's done. I think this is kind of helpful in general. So this is how we reverse a graph, right? You initialize a new adjacency list as E of R, which means reverse, and then for each vertex in V, and then for each edge in E, you just add the reverse of the edge to your E of R, and then you just return it. There's not much to it. It worked exactly the way you would have thought. And so this is just me breaking it down into the format that we use in this class, which is the algorithm, the correctness, and runtime. I would say that this part right here is actually more pseudo code-ish than you should write. The reason why I wrote it this way is just I wanted this to be clear and concise, and this is actually not going to be the type of problem you see on in the class, so it's okay. But generally, you want to say this in words. And then the runtime is all of n plus m because you're going through every vertex and every edge, and so that's your overall runtime. Anytime you have a algorithm that traverses the whole graph, it's all of n plus m. Okay, it is never all of n times m when you're traversing the whole graph. Okay, it's all of n plus m. Anytime you're doing something with just the vertices and don't care about the edges, it's all of n. Anytime you're doing something with just the edges, but you're doing all of the edges, it's still all of n plus m. And the reason is because even if a vertex doesn't have an edge, you still have to go to the head of that adjacency list to know that that vertex has no edge. So let's say, you know, why is my tablet? Okay. Let's say right. So like, even though D doesn't have an edge to anything, you don't know that. You can't like just assume, right? So you're still going, you're going to come to A, and then you're going to look at B, and then you're going to go to C, and you're going to look at D, then you come to B, and then you look at C. And you don't skip this check, right? You still come to D, only to find out there's no additional edges to consider afterward. So it's still O n plus m, even though you only care about edges. Okay. But if you only care about vertices, if you only care about A, B, and D, and I completely forgot about C. If you only care about A, B, C, and D, and you don't care about the edges, that's all of n because you don't actually have to go look at the edges. There's no edge that just kind of dangles out there without vertices. So, keep in mind, get into a good habit of understanding what runtimes are and why the runtimes are the way they are for different steps in an algorithm, rather than just trying to memorize them and not, you know, realizing why that is. Like, don't just look at Dijkstra's runtime and be like, okay, well, that's Dijkstra's runtime. Like, on the actual exam, you should remember it and you should write it down. But understand why Dijkstra's runtime is the way it is a really good way for practicing how to get the correct runtime when it comes to graphs.
I had a question about.
Sorry, I'm gonna read a quick question.
Yeah, so my question was that we have this reverse of the graph, but if we used a reversal somewhere else in our like algorithm, we don't have to detail the steps of the reversal, do we?
No, just say we reverse the graph and all of n plus m. That's good enough. Okay. Someone wanted to see the table of contents real quick. I'll get back to that. Someone asked, we use adjacency lists in the class, and I know it's not necessarily something you can speak on, but has there ever been a case where adjacency matrix was presented for the exam? You will almost certainly always work with adjacency lists. You can assume that we give you adjacency lists. If you then need adjacency matrix for something, you can do that. It's almost never needed. And we will never give you something in adjacency matrix. Okay? All right. Wouldn't you use a nested loop to iterate over every edge, then within the loop, traverse through every adjacency matrix in the linked list? I don't know what that means. An adjacency list is the head of the list is at an array of the vertices of the graph, and then the vertices point to the edges that are has that vertex as the starting point.
I actually said traverse through every adjacent vertex. Yeah, so every vertex, right, has an adjacency linked list, right? So we say that to traverse through all of that is O of n plus m, right? But when I think about, you know, if you just set up like a nested loop where you just went through like a one-dimensional array. That would be n squared, right? But I guess I understand that, you know, I've associated that going through an adjacency list is n plus m time, but I guess I'm having trouble seeing why it's n plus m, because if I were to traverse through that adjacency list, you would create one loop to kind of go through all of the keys of the list, right? And then for each of the keys, you would then have to iterate through the linked list of each of those keys, right? So typically when we're talking about runtime, you know, if it's just like a simple array, that's n squared time, right? Because it's n times m. So I don't understand how, I guess, if you were having to do like a loop to go through every key, and then for every key, you basically iterate through the entire linked list of those adjacent vertices, how that doesn't become a multiplication rather than an addition. Does that make sense?
So, okay. So suppose I have A, right? And I have this just at the very top of my array, and I have B, C, D. Okay. So to go to A, this is my initial part of my my loop, right? And then from A, I go to B, right? So that's one check, right? And then I go to C, so then that's another check, and then I go to D, and that's another check. So that's 3, right? Right. So I mean that it happens to be like that because the A is connected B, C, and D. The A kind of get the very top of the loop gets absorbed into that for loop. Okay.
Okay.
So and now let's say, and it doesn't really matter like what so if I go to B, and let's say that has a points to C and D, right? So now when I get to B, and I go to C, and go to D, right? That's another check and 2 checks, right? So now that's a total of 5. So this is what I'm doing. I'm adding each edge I have to look at in my loop to my I think, because you know, each loop that's underneath the vertex is not a set number of edges. It's not always going to be n edges. In a very sparse graph where there's very few edges, like I might have a bunch of vertices that don't have edges to each other, and I'm not going to pay the cost of looking at every single one of those vertices that don't have an edge to A. Like let's say this graph has 100 vertices, but A is only connected to B, C, and D. So in order to look at every edge that A is connected to, it's a cost of 3. It's not a cost of 100, right? Because I don't actually check all the other vertices. So if you were to multiply it, right, and in a matrix you would, because in a matrix you don't know whether there's an edge there or not unless you check every single cell in your matrix. And that's why we don't use adjacency matrix, because they're actually very inefficient. To check the connectivity, to go through every edge of a adjacency matrix, it is all n squared. Because if there's no edge there, you don't know unless you check. Whereas in an adjacency list, the lack of that edge being in my adjacency list in itself costs nothing, right? Like if I don't check E, F, G, H, I, J, K, etc., I haven't paid the cost for any of that. So it's not n times m, it's n plus m. The reason why it's n plus m and not just m is because there are vertices that don't connect to anything, right? So like if I continue on to this, and I said, like I said, it's like 100 vertices. If I have a C that has no edges, and the D and the E and the F and the G, I can't just discount C, D, E, F, and G. I can't just ignore them. I still have to come to C to find out I have no edge coming out of C. I still have to come to D to find out there's no edge coming out of D. I still need to do E. I still need to do F. I still need to do G. So that's where the O of N comes from. And then checking this B, C, D, C, D is where the O of M comes from. And so when you add those together, you get O of N plus M. Does that make sense?
Yeah. Yeah, I think so. Yeah. So you're almost viewing the O of N and the O of M as like a disjoint, as individual disjointed runtimes that get combined. Yeah. Okay.
Yeah,
That makes
exactly.
sense.
All right.
Thanks.
No problem. Someone else had a question that I might miss. Okay, I answered that one. Okay, was there any other questions that I might have missed? Cool. All right, let's move on. So the next problem that I have on my list is 3.7. Let's go to that. What does 3.7 ask? Bipartite graph. Oh, this one's kind of gross. Let's see. All right. A bipartite graph is a graph GVE whose vertices can be partitioned into two sets, V equals V1 union V2, and V1 does not share a vertex with V2. Okay, so that means that they're two disjoint sets, and that there are no edges between vertices in the same set. For instance, if U of V is in V1, then there's no edge between U and V. So I drew this out earlier. So hopefully you understand what that is. If not, feel free to look it up. I mean, it's a pretty simple concept once you can visualize it correctly. But until then, it can be a little confusing. All right. Given linear time algorithm, determine whether an undirected graph is bipartite. Cool. All right. So this is actually a very good example of what I mean. If we were to present you a problem and we explain to you what a bipartite graph is, and then ask you a question, like a follow-up question, like get an algorithm that finds if a graph is bipartite, that's perfectly fair because we've explained to you what a bipartite graph is, even if bipartite graph itself was not covered in the lectures. Let's see. So part A, my solution. Okay, just like understand, I want to drag this. Right. Set algorithm. So we're gonna create a two-set CNF so that for every edge, E equals V UV, we create this representation where U or V and not U or not V. Run the CNF algorithm through the two-set algorithm, and then if CNF has a satisfying assignment, return true, return false otherwise. And so the reason this works is that if U and V share an edge, then they must be in different sets. So the CNF follows is the following. So if you get a pen. Right. So if U is true, so if we make this true, right, then not U is false. So then we make this false. And if not U is false, in order to satisfy this clause, not V must be true. And if that's true, then V must be false. So basically the idea is that if this relationship forces U and not V, or V and not U. They cannot both be true, they cannot both be false, and therefore they are effectively logically separates them into two separate sets. Okay, we do that with every single edge, and we check to make sure there's a satisfying solution to every single literal or vertex. And if that is satisfied, then we can take every single make two sets of vertices where no edges are within the same subset. So setting this up for all edges means that two set will have to find an assignment such that no two endpoints of an edge are both true or both false, which puts them in different sets. Okay. And so that's how this works. And then creating the CNF is all n plus m, because you're just turning all the literals into, sorry, all the vertices into literals, all the edges into clauses. So it's all n plus m. And then running the two set algorithm takes all n plus m. That's a known runtime. And so overall, this takes all n plus m. Okay. Any questions about part A? Great. Let's see, part B. I'm going to do part B and part C together because they're like pretty short. All right. I want to like put it within view of the. All right. Part B asks, there are many other ways to formulate this property. For instance, an undirected graph is bipartite if and only if it can be colored with just two colors. Prove the following formulation. An undirected graph is bipartite if and only if it contains no cycles of odd length. So we assume the first part, okay, because it was given to us. We're told that an undirected graph is bipartite even if it can be colored with just two colors. If you don't know what that means, a coloring problem it's over here. I wish you have like a graph. It means that I can color the graph and a two color means that I can only use two colors to do this. A three color means I'm allowed three colors to do this. Okay. And so if I was to use, say, red and blue, okay, I do this as red. That means that these are going to be blue, which means that this is going to be red. And now if I get to this last vertex and I say, oh, what color can I make it without it being adjacent to itself? The answer is it's impossible, because if I color it red, it satisfies the, it satisfies the top edge, but not the bottom edge. And then if I color it blue, it satisfies the bottom edge, but not the top edge. So it's not possible to do this graph in two colors. Okay, so that's what a coloring problem is. And so part B, the answer is that any long cycle can be separated into two sets by using a different color on each neighbor. Likewise, an even cycle can be separated into two sets because each neighbor can be assigned a different color without conflict. So that's kind of like, if you think about it, right? Like if you had an even number of vertices that's in a cycle, then every other color can be one, every other vertice can be one color, and every other vertice can be a different color. So, and then if there is no cycle, then you can just basically go alternate colors and it would never, you wouldn't have a problem. So what that would look like is that if we were to erase this, without a cycle, I can go on forever and just use a different color because I'm not going to come back around and have a conflict. And the other way to look at the other part, second part of it is that if this cycle is an even color, I can always just use alternating colors and it will work. Okay. So, so using the above, we were, if we were to insert an odd vertex into an even cycle, there would be no way to color it without causing a conflict. And I showed that using the graph of this, right? Like there's no way I can make that color anything without a conflict because it's odd. Okay, so it says prove the following formulation: an undirected graph is bipartite if and only because if it didn't cycle back, right, that's allowed. This is fine. But the second that we have this odd cycle length, we're in trouble. Okay. And then so part C asks, at most, how many colors are needed to color an undirected graph with exactly one odd length cycle? And the answer is I just need one more color to do this. If I was to use let's go with green. I can't just erase that. Okay, you know what? That's fine. We made this green. We're able to complete any odd cycle with a different color, and that's how that works. So that's 3.7. With a solution where you apply DFS to the graph to get a topological sort and previous array work, you would iterate along the sort and set the color for a vertex to be opposite the color of its previous. Blue if there's no previous. You do this because it is a necessary but not sufficient condition for a vertex to have a different color than its previous to be bipartite. When this is done, you iterate through all the vertices and edges in O(n plus m. Time to check that the coloring does not conflict. With a DFS using post order numbers. Wait, no, not using post order. Okay, so first of all, you can't topologically sort the graph because you don't know if there's cycles or not, right? Part of this problem is saying, what do you do with even and odd number cycles? So you can't do that. You can't topologically sort a graph. And the second thing is that give a linear time algorithm to determine whether an undirected graph is bipartite or not. And topological sort only works on a DAG. So it's not acyclic and it's not directed. So no, neither of those things can, none of that can happen. Okay. And this is what I'm talking about. Like, you have to understand what algorithms can run on what type of graphs, because just knowing that this is a undirected graph means that you can't topologically sort it. So that's like should not even be an option. Okay. All right. Moving on to next problem, 3.8. All right. 3.8 is a really silly problem, and I'm just gonna go over it pretty quickly. I don't feel like we should spend too much time on it because it's such a silly problem. I think it's also in one of the Die Hard movies, so go watch the Die Hard movie for a solution. Is it 2? Is it 3? Which Die Hard movie is the one with Samuel L. Jackson and 3? Cool. Die Hard 3. All right. So pouring water. We have 3 containers whose sizes are 10 pints, 7 pints, and 4 pints, respectively. The 7 pint and 4 pint containers start full of water, but the 10 pint container is initially empty. We are allowed one type of operation, pouring the contents of one container into another, stopping only when the source container is empty or the destination container is full. We want to know if there is a sequence of porridge that leaves exactly 2 pints in the 7 or the 4 pint container. Model this as a graph problem, give a precise definition of the graph involved, and state the specific question about this graph that needs to be answered. Okay, so A is we will model a graph in such a way that each vertex represents a possible configuration of the 3 containers. That A1, A2, A3 be the amount of liquid in the 10, 7, 4 pint containers. So A1 plus A2 plus A3 equals 11, since we start with 11 pints of water. Add to each vertex a directed edge to each configuration possible from pouring the contents of the containers based on the problem description. There are many ways to determine these values, but one such way is to take the current configuration and add a neighbor when A1 is poured into A2, and then another neighbor when A1 is poured into A3. Do this again for A2 and A3 into the other two containers. This gives us all possible neighbors. There are at least most 6 neighbors. Continue to do this for each vertex until no bridges exist. Remember what I said that a bridge is that we are done with all the different connecting of how we create this graph. And so this graph is going to look somewhat like, where did I paste this problem? The heck, what did this? Okay. My app stopped syncing and doesn't see this. Oh, there it is. Okay. That was weird. So basically what this means is that we start with some like node. So we are going to be here and we start with, hold on, what did it say? 7 and 4. So we have 7, 4, 0, which represents our 7, 4, and 10 pint containers. Okay. And so that's our first node. Now, what would happen if I pour 7 into 4? I can't pour the 4 into 7. But what I can do is on my next configuration, I could do 0, 4, 7, right? I can also do 7, 0, 4. I think those are the only 2 possible paths. Okay. And then my 0, 4, 7, I could pour the 7 back. I could pour the 4 back. I can also pour 4, 0, 7. And I guess these are all going to be undirected because well, is that true? No, it's not undirected because some things can't go backwards. Okay. This can also become 0, 1, 10. Okay, so you get the idea. You basically just sprawl out your graph, and then every configuration that you can go from one to the other, you're going to think it out and you do it, and then eventually you get to the question you're asking. From 0, 7, 4, can we reach a vertex that is star 2 star or star star 2, where star is any number? So can we get to a point where the first container is 2 or the second container is 2, and it doesn't matter what the other containers are? And so part B is what algorithm would be applied to solve this problem. We can run explore with our newly constructed G, where with the starting V is 0, 7, 4, and we return true the moment we reach a vertex that is either star 2 star or star star 2. If we do not reach one by the end of the explore run, we return false because no such configuration was reached. The other thing you can really do is, like, as you're drawing this graph, because your graph is basically you sprawling out an explore situation, if you somehow get to a point where you're drawing one of these configurations, star 2 star or star star 2, you can just end. You can just say, yep, I can reach it because I've shown that I can follow this path of pouring and get to it, right? In fact, what's interesting is that if you draw out this entire graph and run a BFS, you can actually find what the a possible solution in the least number of pours, right? So if you like, you can some variations of this problem is like you can only pour from one container to another 7 times. Can you get a container to hold 2 pints? And the answer would be yes or no. Right? So that's kind of cool. And then part C asks, find the answer by applying the algorithm. I'm not going to do that. I think that's silly. I think if you really want to, you can draw it out yourself. But I'm pretty sure the solution ended up being it can be, if I had to guess. Okay. Someone asked, this feels like a gotcha question because the object in question is something that flows, but the optimal solution is representing each state of the container as a vertex in a directed graph rather than a node in a flow network. First of all, I didn't write the problem, so I'm not trying to trick you. But I mean, I think you just need to be careful. I think there are going to be questions like worded in such a way that, you know, if you're paying attention to what the problem is without like, instead of like just trying to memorize like the one and only approach to the problem, I think it's fair, right? I feel like yeah, I feel like don't just get tricked by the topic of the problem, but actually try to understand how a problem is solved. Okay. Hi, Emily. I just noticed Emily answered the question for me. All right, that's the next problem. 3.11. Emily, just so you don't hear it from anybody else, I was making fun of you about how you said you had ugly handwriting. I told you I was going to, so I think it's fair. I had discussed this with Emily before because I thought it was funny that she, that she made that comment. All right. So next problem is 3.11. Cycle containing E. All right. Let's see what 3.11 is asking. There was a few of these problems that I had to answer for the first time while getting ready for this office hours. I love seeing problems that I've never answered before. Again, because this is kind of fun for me. So I don't know if this is one of them. Design a linear algorithm which, given an undirected graph G and a particular edge E in it, determines whether G has a cycle containing E. So I actually didn't have like a formal solution to this. I just kind of knew the answer to this, and some students had asked about it in ed in previous semesters. So I never realized it was like an actual like DPV problem that does this. So here's my solution, and then I'll actually kind of draw it out to help illustrate what I'm talking about.
Hey, sorry, I might have missed it, but did we ever cover what the runtime was for the pouring water example?
Let me see. I did not, because this wasn't like asked in like the format of the class. This is just like I answered A, B, and C. But to do this, it would be O to the number of configurations and the number of ways you can get from one configuration to the other. Oh, that would be the runtime. So O of n plus m. Because you're basically drawing the graph based on how you know that graph can be formed as you're doing the explore.
Cool. That aligns with my expectations. Thank you.
Okay, great. So in order to answer 3.1 is that we're going to remove this edge, right? And this is one of the strategies and tips I talked about in the previous in the slides, is that if you're given a special edge, consider removing it and seeing what you can do with the graph without it, right? So what I'm going to do is I'm going to remove this edge completely, and then I'm going to run explore from U to get back my visitor array. And notice how I use explore, not DFS. I use explore because I care about connectivity from U. And then check if I can get to V from U or not. If it's true, then E was part of a cycle. Otherwise, E was not part of a cycle. And the reason for this is that by definition, if E was part of a cycle, then there exists at least two unique paths from U to V. So every single vertex, or every single pair of vertices within the cycle, has to have two, at least two paths from one to the other. it's what defines a cycle, but at the same time, I think it'd be good to just sort it out. So like in a very basic cycle, right? Like if I had no other information about it, if I had A, B, C, D, and these are a cycle, right? This is the most basic of cycles, right? Like you can have like other edges coming off of it. This can be part of another cycle. It doesn't matter, right? It doesn't really matter. All I care about right now is A, B, C, and D. It's part of a cycle. I know it's part of a cycle. So to get from A to B, I can either go A to B this way, or I can go A to B going this way, right? There's always at least two paths between any two vertices inside of a cycle. In an under let me think. Yeah. Okay. Does that make sense? I think that's only true on director graphs. Let me think. What happened to director graph? I think even in a directed graph, technically it's true. Like even if you like go from into a circle, like it would still count as a separate path, right? Like you can go over the same vertex. Like you can just cycle around a few times and get there. Yeah. Yeah. Okay. Yeah. So yeah. So there's at least two. Okay. And because we know that, if we remove E, if we remove the edge E, we have removed at least one unique path from U to B, and that is over that edge E. But if we remove that edge, and if there's still a path from U to B, then there were at least two paths to begin with. And so E is part of that cycle. And so if we wanted to look at it here, right? So this is the even more basic of a cycle, A, B, C, right? So if we consider E equals A, B, okay, there's a cycle. If we remove A and B, the edge A, B, but there's still a way for me to get from A to B, then there's a cycle because I've removed one of the paths, but there's still a second path, and therefore it was a cycle. Okay? And so having said all that, the runtime of removing a edge is O of M because you have to find it in an adjacency matrix, adjacency list. You have to find that edge, and then running explore is O of M, and so your overall runtime is O of M. It's also fine if you say it's O of N and then plus O of N plus M, because like the runtime here can be kind of mix and match. I think it's the most correct is O of M, but if you said O of N plus M, that's also fine. Okay, isn't removing an edge O of N plus M? It's actually O of N or O of M. Either is correct. I tend to use O of M when I'm working with edges because it makes the most sense to me. The reason why it's either O of N or O of M is that if I had the adjacency list of A, B, C, D, whatever, right? If I wanted to remove A, B, it's O of 1 for me to get to the first endpoint. I'm not showing the actual thing I'm doing. It's O of 1 to get to the first endpoint, and then A can be attached up to M edges or up to N vertices. And because of that, O of M or O of N are both technically true. I just use O of M whenever I'm working with edges. It's easier for me to remember. Okay. There should be a post. Yeah. Thank you, Nicholas, for linking it. I'm assuming that's the link to the post about about graphs. Yep, and hopefully graph runtimes for removing an edge is open or open. Yep, and then it gives you additional information there. Okay, cool. All right, so that is 3.11. Yeah, so just remove the edge, run explore, see if you can still get to the vertex of that edge. And if you can, then there's a second path. And if there's a second path, then by definition, there's a cycle. 3.15 Computopia. Okay. We didn't give you solutions to 3.15. Was there a practice solution to 3.15? Anybody know?
I'm checking.
Oh,
yes, we did.
Okay.
We did. Thank you.
All right. Is it okay if I skip 3.15 so we can get a little more done?
Yeah, sure, please.
All right. How about 3.16? Did you get a solution to 3.16?
I don't think so.
All right, 3.16. CS curriculum. All right. Someone said yes. Where is the solutions? Maybe I can just take a quick look. Okay, no solutions. Okay, that's fine. All right, 3.16. CS curriculum. All right. So 3.16 asks, suppose the CS curriculum consists of n courses, all of them mandatory. The prerequisite graph for G has a node for each course and an edge from course V to course W, if and only if V is a prerequisite for W. Find an algorithm that works directly with this graph representation and computes the minimum number of semesters necessary to complete the curriculum. Assume that a student can take any number of classes in one semester. The running time of your algorithm should be linear. So the way you think about this is that we have an edge, say VW. If you have to take class V before class W, you can't take them together, so they can't be taken in the same semester. Okay, and then if you have another edge WX, this would take 3 semesters. You have to take V one semester, W the next semester, and X the semester after that, right? And then if you have X and Y, this would take 4 semesters. Okay, that should all start to make sense. But if I had a second what's it called, prerequisite to W, let's say A, right? So in or some this is actually pretty rare these days, but especially in the graduate level. But in undergrad, sometimes you have to take 2 different prerequisites in order to take a class. So for the class W, I have to take V, and I also have to take A in order to be able to take W. Now, V and A don't depend on each other, so I can take V and A in the same semester, followed by W immediately. So that would take still 4 semesters, even though I've added an additional prerequisite to W, because I can take in semester 1, I can take VA. Semester 2, I can take W. Semester 3, I take X. And then semester 4, I take Y, right? So any situation where I have 2 classes that are both prerequisites to one class, as long as there's no other prerequisites to those classes, I can take those 2 together and it's fine. Okay. So that's 3.16. Let's look at what the solution would look like. 3.16 is actually kind of funny because it is actually somewhat of a dynamic programming problem as well as a graph problem. Okay, so that's my conclusion. So first, we're going to topologically sort the vertices with DFS. And then we're going to start with all vertices as a count of 1. That means it takes 1 semester to take all these classes, okay? And then we're going to start from the very first vertex, because we know this is a source, right? We know that the first vertex of a topologically sorted DAG is a source. We also know this is a DAG, by the way, because you cannot have a cycle in this graph. It wouldn't make sense for the cycle for there to be a cycle, right? If I have to take V to take W, and then I have to take W to take X, if I have to take X in order to take V, then I could never start with any class. It's like that joke that people have. It's like, you know, you need you can't get a job without experience, and you can't get experience without a job. So you can never really get a job. That's a sad joke that people tell. So yeah, you can't do that with a class. So this has to be a DAG. Any cycles in this graph would make 0 sense. Okay, and because of that, we can do a topological sort. And then what we're going to do is that starting from the first vertex, which is a source, for each vertex it has an edge to, increment the end vertex by 1. Okay, then we go to the next vertex, U, and for all the vertices V that U has an edge to, if the count V is less than or equal to U, then set the count of V to U plus 1. Okay, I'll go over this, what this looks like in a second. And then we just return the largest count. And the reason this works is that because classes must be prereqs in a chain, there can be no cycles. And since there are no cycles, we know the graph is a DAG. Since it is a DAG, we can topple sort the graph and know all classes that are a prereq into a class are lined up before it. So again, this is, I think, what some of the students missed in the homework is that you have to explain why you can topologically sort, or why you can run DFS, or why you can run Dijkstra's on the graph. You have to kind of explain the nature of the graph on why you pick your black box. And so because I know that it's a DAG, I can topologically sort it. Okay. And then from there, we know that the class that takes the most semesters to complete, the prereqs for will be deciding how many semesters we need to complete. This is equal to the longest path in our DAG. Our algorithm finds the longest path, and the length of the path is the number of semesters we need. Finding the longest path on a graph is actually a really difficult problem. It's NP hard. But finding the longest path in the DAG is actually super easy. It's actually a linear time algorithm. Small tidbit, you don't really have to worry about it for this exam, but if you were to find the longest path on the DAG, this is how you would do it. Because you know that each any such chain has to go from left to right, from source to sink, you can increment how long it takes us to get from one vertex, you can increment how long that path is. So let's consider. Okay, and let's just draw a bunch of, I don't know, doesn't really matter. Okay, so what is our longest path? If we just look at it, I think it's 4. So A to B to C to E to F. So our longest path goes 4. Okay. And so how we want to do this is, if we start off with A equals 1, B equals 1, C equals 1. Right. So our algorithm starts off by setting everything to 1. Okay. Now what we want to do is that for everything that starting from A, everything that A can reach, we increment that number by 1. So wait, is that right? Should these be 0? Sorry, hold on. think these should all be I think it starts with 0. Sorry. Sorry. I'll fix that in my post. Okay, so these start at 0. So for A to go to B, we plus 1 on that, and then we're done. Oh no, A to C is also 1. So how many edges does it take to get to B is 1, and how many edges does it take to C is also 1. Now the next step is to say, okay, now that we're done with A, we go to B. For everything B can reach, we want to see if we can get a longer path, right? So B goes to C, that's 1. And it is let's see, less than equal to, right? What's my step? And for all vertices V, you less than or equal to. Okay, so we B to C, B is 1, C is 1, they're equal, so we want to increment C by 1. Okay, so that's another plus 1 there. And then B can't reach anything else for C. C goes to D, C is 2, D is 0, so we want to increment D by 2, by 1. Oh, set it to U plus 1. Okay, so it's C plus 1, which is 3. So D is equal to 3. Okay. C to E, E is 0 compared to the 2 in C. It's less than, so this is plus 3 as well. And then F, we cannot reach. Okay, so then we move on to D. F is set to 0, which is less than the 3, so we increment that by 1, so this is plus 4. So then this gives us a grand total on the longest path. A is 0, B is 1, C is 2, D is 3, E is 3, and then F equals 4. And so the longest path is from A to F, giving us a total of 4 semesters, which means that we have to take classes A before B, before C, before E, before F. So it takes us 1, 2, 3, 4. Oh, that's why I started at 1. Oh my gosh. I want to start at 1 because A takes 1 semester. Even though it's a path length of 0, it takes 1 semester to take 1. So that's why I did that. I'm sorry, guys. Past Joves was a little bit smarter than current Joves. So 1 semester there, 2 semesters there, 3 semesters there, 4 semesters there, 4 semesters there, 5 semesters there. So it takes 5 semesters to complete our degree. Okay? Does that make sense to everybody? We want the longest path because whatever the longest path is it's going to overtake all the other chains that we have to take. All the other chains can be taken alongside our longest chain, and so getting that longest chain is what our answer is.
So
Sorry,
the
can I
longest.
ask you? Oh, sorry.
The
go on.
longest path is 5.
Yes. Well, the longest path is 4, but it takes 1 semester to do the first class. So it's a total of 5 semesters, but the longest path is 4 edges. Does that make sense?
Okay, that clarifies. Thank you.
Okay, yeah. The longest path is 4 edges, but it takes 1 semester to take the first class, and therefore it takes 5 semesters to finish the program. That's not what the question asked, but if you wanted to backtrack, you could. I guess you could do that. So let's see.
I guess this kind of has the assumption that
So first semester we would take
in the same semester, right?
Yeah. So first semester, we are going to take A. Semester, we're going to take C. Fourth semester, we are going to take D and E because D and E both come after C. And so we take this semester together. And then the last semester, we can take F. Alternatively, if we don't feel like doing that, we can also take F and D together. So D can come, you can take D whenever. It's just one of those like classes that you don't have to take with E. You can take it with F if you feel like F is the easier class and you want to double up the last semester.
Thanks.
And that's why the longest path matters, because we know that we have to end with F and we know that F comes after E. Whether D is done on the fourth semester or the fifth semester doesn't matter, because the longest chain is A, B, C, E, F.
Can I ask you something?
Yes.
Does this method of counting the longest path that you're showing here on the topological graph, is this like can we use this in general to find out the longest path on any topological sort?
On any topological sort. So if you have a topological sort, that implies you have a DAG. If you have a DAG, you can use this in order to find the longest path. Yes.
Thank you.
And then the runtime of this is O of n plus m, right? Because topo sort is O of n plus m. Finding the longest path is O of n plus m on the topological sort. And then finding the largest count, like if I'm checking to see if A, B, C, D, E, F has the largest count, it's O of n, because I'm checking all 5 vertices. And then so the overall runtime is O of n plus m, which is considered linear in terms of graphs. All right.
One last clarification. For here, the longest path is from A to F, right? And with the topological sort, we can find longest path for any given vertex, knowing that we have the sort, the topological sort.
Yeah.
Is that a correct statement? Yeah. Okay.
For a topologically sortable graph, which is a DAG, doing this algorithm will get you the longest path to any vertex. And then you want the vertex with the longest path, which determines how many semesters it takes.
Thank you.
Okay. Everybody good? Silly question. We mark visited on C when we go from A. Then when we go from B, don't we avoid it? Well, I'm not running DFS. I'm just running sort of like a custom counting dynamic programming algorithm. I don't avoid it because I'm not doing DFS or Explore. All right, next question is 3.22. Reachable from all vertices. Funny enough, I think my handwriting is actually a little bit better today because there's less lag between me putting my pen on my tablet to my network. So like my marks aren't like as connected as it was. It's still ugly, but it's like not painfully ugly. I think. You might not think so. All right. 3.22. Given an efficient algorithm which takes it as an input directed graph G and determines whether or not there is a vertex S from which all other vertices are reachable. And this is exactly what we talked about, right? I said, you should try to see what happens when you reverse the graph. Anytime you have a question where it's like, can everything reach something? You might want to consider doing a reverse for that. Okay. Let's see. All right, so we're gonna run the SCC algorithm on G. And we're gonna get back this metagraph with G, SCC, V, SCC, E, SCC. You don't actually have to write this when you're doing this this kind of problem. I just like to sort of mark it so it's easier for me to reference. And then we're gonna check to see if the metagraph G has a single source SCC. That is an SCC with no incoming edges, and that there's only one such SCC. To do this, we will create an array representing each SCC node and set the value to false. We will then go through each edge in the SCC metagraph. For each edge, we mark V as true to indicate it has an incoming edge. So if edge is UV, we mark the endpoint as having an incoming edge. And at the end of the check, any node that is false is a source SCC. And then if there is only one source SCC, then we return true, otherwise return false. A different way to do this is you can also, if you wanted to, reverse the metagraph once you have it, and then check to see if there's any node with no outgoing edges, which is a faster check because with adjacency, well, not a faster check because you still have to reverse the graph, but you can do, it's easier to say, check to see if a vertex is a sink by saying that it has no outgoing edges. But this works just as well, and I think it's easier to understand. So yeah, if there's only one source, then that's true, otherwise false. And the reason for this is if there's only a single source SCC, then they can reach all other SCCs because all SCCs must have a source. And if there's only one, then all SCCs can be reached by that one source. And if there are two or more source SCCs, then they cannot reach each other since source SCCs cannot be reached by other SCCs. So these are the definitions of source SCCs that I'm going to use here. Any source SCC cannot be reached from outside that SCC. That's a fact. A source can only reach other SCCs. It cannot be reached by other SCCs. 2, all SCCs have to be reachable from some source. You have to start from somewhere to get to the SCC. So all SCCs have to be reachable from some source. Now, if there's only one source, then in terms of like, logic, those two things combined, it says that one single source can reach all SCCs. And so the SCC algorithm is all n plus m. Check for source SCC is also all of n plus m. So your final runtime is all of n plus m. Questions about this solution? And I'm sorry, I said about the reversing thing. From which all other source. This is actually does not need that that approach. I think I do have a problem that needs that approach, but this is not one of them. Not yet. Okay.
Just a question. Is the SCC algorithm always giving us back the metagraph?
Yes.
And the metagraph, how is it represented internally? Is it a bunch of nodes?
It's an adjacency. It's so you don't have to worry too much about it, but you can think of it as an adjacency list of the meta nodes, and the meta nodes are just the CC nums of each of the strongly connected components. And then when you look at the CC num array of a given vertex, you know what SCC it belongs to.
So we can assume that all the nodes in one strongly connected component is a single vertex when we are formulating the solution like you did.
Yeah, you can assume that the SCC is one single vertex that you're working with in the metagraph.
Okay, thanks.
And in fact, this question only asks if there's a single, if there's a vertex S such that all other vertices are reachable, and the answer is yes or no on this. But if you were asked to identify all the vertices that can reach all other vertices, it's actually if you have a single source SCC, all of those vertices can reach all other vertices because every single thing in the source single source SCC can reach everything outside of the SCC, and everything within that single source SCC can reach each other. So by definition, if any vertex in that single source SCC can reach all other vertices. Yep. hand up in chat.
Oh,
is there a question?
Sorry. I think that was for earlier, but actually, now that I'm talking, so for this question, I said, I did run SCC and get the metagraph, and on that metagraph, do topological sort, and if you run explore from whatever is in the first of whatever the first vertex in that topological sort is, and it can't reach every other vertex in that topological sort, then there is not a vertex V that can reach, or sorry, a vertex S that can reach everything. And I'm not sure if that is correct.
That is also correct. So what you have basically done is you've decided that I am going to take the first vertex, which I know is a source. And if this source can reach all other vertices, then we are done. We have
Something
found
in there
that this
can reach all other vertices, yeah.
Exactly.
Okay.
And that does work. Because any vertex that it cannot reach, by definition, is also a source vertex. Or
okay.
It's also either a source vertex or it's a disconnected. The graph isn't connected, which this problem can allow for that. And then in that case, it also can't reach all the vertices. So yes, that actually is also a good approach. Probably better approach now that I think about it. Any other questions?
So if we say that we get the topological sort in this directed graph, the very first node it have to be a source node.
Yes.
Yeah, a source. Then that's it, right? If we find at least one source, then the answer would be yes.
No, you have to make sure it's the only source. You could have two sources, and the answer would be no.
But it's asking whether or not there is a vertex. We found one.
Well, no, because okay, so suppose I topologically sort my graph. Right, this is a legal topological sort. I know that A is a source. But the answer to this is no, because A can't reach B and B can't reach A. The fact that I have two sources means that this is a no. I do not have a vertex that can reach all other vertices.
It have to be a source SCC.
It has to be a single source SCC. I have to have a single source SCC. If I have more than one source, the sources can't reach each other. So
does this mean that
if this instead looked like this, A is the only source SCC, and then yes, A can reach all other vertices. However, without that, A and B are both source SCCs. A and B cannot reach each other, so there are no vertices that can reach all other vertices.
So could we say that if there is a unique path in your topological sort, then you are guaranteed that you have a single source, and then you can use the topological sort to do the problem, right? So you can constrain it like that.
If you have a unique topological sort, yeah, you could say that. That would be like trying to solve a much more complicated problem in order to solve a simple problem. But yes, that would be true. Wait, hold on. No, because the reverse may not be true. So you can't do that. So what could happen if I was to do this instead? So okay. This does not have a unique topological sort. ABC is a valid sort, ACB is a valid sort, but at the same time, this graph right here, A can reach both B and can reach all other vertices. So no, just verifying, you're gonna have a false negative because you don't need a unique topological sort in order for this to be true.
Got it. Thank you.
All right. I'm going to cover 3.24, and then I am going to take a break because that'll finish up chapter 3. Okay.
Quick question.
For a break. Yeah.
So for the last question, we have to mention that the reason why we can run the SCC algo is because it's a DAG, right? It's a DAG, right? In the JOC.
No, we have to run the SCC algorithm because it's not a DAG, and we can't make sense. We can't we can't understand really well the connectivity of this problem without. In fact, actually, no, you don't even have to get a topological sort. Wait, well, sorry, what was the question? You asked, sorry.
If do we have to mention JOC that the reason why we can run the SCC algo is because our graph is a DAG?
Well, our graph isn't a DAG.
Okay.
So yeah, it's not a DAG. You can run an SCC algorithm on any direct graph. It does not have to be a DAG.
Gotcha. Thank you.
But the reason that we run the SCC is because we are given a directed graph and we want to determine the connectivity.
Yes.
Is it how we interpret the questions? Okay, thank you.
Yes. So, okay. Someone in chat asked, wait, Joves, did you say you don't need to run a topological sort? There are two approaches to this problem. There's this approach of finding out if you have a single source or not, which is the approach I did. I did not do a topological sort in my solution. I don't care. I'm going to check every vertex and see how many sources there are, right? The second approach, which a student brought up, was that if I do a topological sort, I can get a source at the very beginning of my sort. Then I run explore on that source and see if that source can reach all other vertices. If that source can reach all other vertices, then it is a single source SCC. If that source cannot reach all vertices in my explore, then it is not a single source SCC. And in doing so, they need to find that first source. And that's why they ran a topological sort, which is a perfectly fine solution. I didn't have to do that because I'm going to check every single vertice to see if it's a source or not. Okay. But I thought the output of the SCC is the metagraph, which is a DAG of the SCC. Yes, the SCC output is a metagraph. It is a DAG, but you don't need it to be topologically sorted. A DAG doesn't necessarily mean it's topologically sorted. So in some situations, you do need it sorted. In some situations, you don't. So I think the confusion is that there's two different approaches to solving this problem. One of which you do want it topologically sorted so that you can get immediately access to the first source. Because I'm going to check every vertex to see if there's a source anyways, I don't need to know what that first source is. I hope that's not confusing for students. I hope go back, try to rewatch the two different solutions. Hopefully that makes sense. All right. Moving on to the next problem, which is 3.24. Yep. Everybody go look at chat. Thank you to Clint for summarizing the two solutions. All right, cool.
And I guess I just want to confirm that both solutions are equally valid, right?
They are equally valid. Correct.
Thank you.
$3.24.
I think the question is both solutions optimal and acceptable?
Yeah, they're both all n plus n. They're both correct.
you.
They both get you the solution. So yeah. I'm not going to take a negative 10 points just because it's not the solution I did. That would be cruel and unfair.
That's assuming you grading the paper.
So so the way we grade problems to begin with is that one of the TAs, it's usually me, but it's a different TA this semester because I'm not actually like technically TAing the class. They write a model solution. So they write a solution that is the most like obvious or the most popular way to solve the problem. And then they'll write alternate solution. They'll say, this is not the only solution that can work. Here is some known alternative solutions to this problem. If this problem was given in homework, both of those solutions would be put onto the model solutions. One as, this is the first solution, this is the second solution. Beyond that, however, if a TA reads a solution that they go, I think this will also work, they will post about it, and all the other TAs, several of the TAs will take a look at it and confirm whether it works or not. They'll try to poke holes in it. They'll try to say, yeah, it can work. They'll prove that it works. And if it becomes a solution that says, yes, we can confirm that this works, we'll make an announcement to the graders and say, this is a third solution that can work. Keep an eye out for this. And then if a TA has seen that solution and thought it didn't work, they will go back and mark it as correct. Even if a solution has a mistake, but the approach is correct, we will update our list of solutions with the third solution. So don't worry about whether you present a solution that isn't the one that I came up with immediately. If it's a valid solution, you will get your points for that solution. Even if it means that you have to tell us during the regrade feedback and like, hey, I actually think this does work. I think you misgraded this. It will pull in additional TAs to take a look, and we will say, yeah, it actually does work, and we will give you credit for it. Contrary to Reddit posts, we do not simply say, does this match the one and only solution? If it doesn't, you get 0 points. That's not how grading works. It would be unfair.
That's very reassuring. Thank you.
Good. No. All right. Let's see. 3.24. All right. Give a linear time algorithm for the following task. A directed acyclic graph G. Does G contain a directed path that touches every vertex exactly once? I don't know if you guys noticed this. I put in when I write these notes to myself. These are from like my notes. Some of them as a student, some of them I added to as a TA. I like to put in like the general approach of what I'm going to do into my little summary here. So that one says topple sort. This one says SEC. This one says topple sort. So that it's a good way to because what you end up doing is like when you're going studying after you have all these additional problems that you've worked out, and you want to be like, oh, I want to brush up on my use of BFS, right? Then you go through your list of problems that you've typed up or put into your notes, and you go, okay, that's a BFS problem. This is a BFS problem, and that'll kind of get you like a more focused studying session rather than having to read all 20, 30 problems over again to see which one was BFS. Okay. Let's see, 3.24. Okay. Some students said that this is similar to the unique topological ordering, and that would be true. that if there is a solution to this problem, it is only if and only if there is a unique topological ordering of the DAG. Yes. Yes, because it's a DAG, so you can't flip places as long as they can reach each other. All right. This is my solution. All right. Run the DFS-based topological ordering algorithm on the DAG. And again, you can say this in a number of ways. You can either say run DFS and get the topological ordering, or run the topological ordering algorithm on the DAG and get back to topological ordering, or run DFS-based topological ordering. Like, the important thing is that you understand that there's an algorithm that helps you get the topological ordering of a DAG, and it's based on DFS. However way you want to word it, we're pretty okay about that. We denote this array as T with n vertices, and this array is sorted from source to sink. Yeah. And then check if, from left to right, T of I and T of I plus 1 is an edge for all 1 to n minus 1. And then if all checks return true, then return true, return false otherwise. Basically, you have your topological ordering, and you want to check that between every vertex from left to right, that there is an edge between them. Okay? You don't have to be like formal and descriptive like this. You can just say, for your from your source to your sink of the topological sort, make sure that every adjacent vertex has an edge from one vertex to the next. Okay. And then the correctness is that step 1 is a known algorithm to get topological ordering of a DAG. We know from this topological ordering that if U of V is an edge in E, then U comes before V in the ordering. So that's by definition of what a topological sort does. And then so if T of I has an edge, if T of I does not have an edge, T of I plus 1, for some I, then we cannot reach T of I plus 1 from I, right? Because there's no edge. And our path must backtrack to an earlier point that can reach T of I plus 1, or T of I plus 1 is the start of a new source node. So we don't have a directed path that can reach all vertices. If you have to backtrack, or if one of the nodes is a new source node, then you don't have a path that goes from beginning to end that can reach all vertices. And the runtime is DFS-based topological ordering algorithm is O of n plus m. Checking that there's a edge from all adjacent vertices is O of n plus m as well, and so over runtime is O of n plus m. Okay, any questions?
I have one question regarding the runtime, not for this specific question. My question is, when do we need to simplify the runtime? For example, we know like express the runtime in terms of n or m. Can we always assume that the graph is connected so that m is greater, is at least the order of n?
You should never, ever assume the graph is connected unless we tell you it's connected. It's an MST problem. It's a max flow problem. Because MST problems and max flow problems only make sense if the graph is connected. And if we tell you the graph is connected, you can assume that. Otherwise, you can never assume that the graph is connected. You should only simplify if you know the graph is connected, or if you know something specific about the graph where n is greater than m or m is greater than n. If you cannot make that assumption, then you need to give the runtimes in both, in terms of both.
So MST and matching, right?
MST, in the MST problem, you will have m is greater than or equal to n minus 1. And so at that point, you can say O of m for all your different runtimes and you'll be okay.
Oh, okay. And the second problem is the matching problem, right? You can assume it's connected.
The second problem is the max flow problem.
Oh, max flow. Okay, I see. Thank you.
And that's only if we give you a max flow problem to begin with. If you take a graph, like a graph that might be about part type, and then you say, I'm going to put this through the max flow algorithm, that starting graph is not a max flow, it's not a flow network. You have taken a graph of unknown connectivity and changed it into a max flow problem. So you cannot assume that that initial graph of unknown connectivity is connected simply because you turned it into a max flow problem. Similarly, you cannot take a problem of unknown connectivity, change it into a MST problem, and say, oh, because it's an MST problem, the graph is connected. That's not how that would work, right? You've made the changes to use a black box. You cannot assume that the input we gave you was meant for an MST algorithm.
That is fair.
Okay. I have one hand up in chat.
Yeah, I just wanted to ask, is it possible to also check if the DAG has a single sink vertex?
Nope. So if I had A, B, C, oh, where's my drawing? Oh, oops, I didn't scroll down. Okay, sorry. So if I A, B, C. C here is a single sink, right? I do not have a path that can touch all vertices. Yeah, a single path, right? Like I don't have a path that can touch both A and B, but it has a single sink.
Okay.
Okay, I'm gonna write it so that students don't see this and make a mistake. All right. Any other questions?
So for a directive acyclic, for a DAG, we can only assume, well, by being a DAG is have no cycle. Anything else we need to run appropriate algorithm for connectivity. That's the only thing that is given for a DAG, no cycle. That's it. Anything else that we need to do, we need to run the appropriate algorithm.
Correct. Because
that's all we know.
Yeah. This is a valid DAG.
And they're not.
It is directed, it is acidic, yep, and they're not connected. In fact, you can, that is also a valid DAG. E can have no edges at all, and it's still a valid DAG. Okay.
Thank you.
Can I have a?
On this graph that on this graph I just wrote with this A, B, C, D, E, how many sources are there and how many sinks are there?
Three sources, two sinks.
3 sources and 2 sinks.
Three sources and 3 sinks.
That's correct.
Wow, actually we have to run DFS.
Right. So this is a source, this is a source, this is a source. This is a sink, this is a sink, this is a sink. You have 3 sources, 3 sinks, 5 vertices. So be careful. A single vertex or SEC that's an island is both a source and a sink. All right. Anybody else have questions?
Suppose I have a tree and it is a direct tree. Can it have a circle, but it's not a direct circle? I mean cycle. For example, maybe you cannot follow the entire cycle along the directions, but if you ignore the direction, it can form a circle, a cycle.
The tree property provided half a cycle. Because you can only have
tree,
n minus
tree cannot have a cycle, but if it is a indirect tree, it cannot have a cycle. But it is a direct tree, and you have a cycle, but you cannot traverse this cycle following the directions. Is that still a tree?
I don't know. I don't know what a directed tree is. I don't think a directed tree makes sense or is something that's like we care about or do. A tree, like just saying a tree by definition is undirected.
Okay, thank you.
I have a question regarding the runtime. So the second runtime, which is O n plus m, Why is it ON plus M for checking consecutive edges if they have a directed edge? Shouldn't that be O of 2N since the size of the topo sort is 2N? Why is it ON plus M? Just wondering.
Because you might have like multiple edges, right, in a DAG. Like, let's see. Like if I had A, B, like there's multiple edges, and then this can have multiple edges as well. Like, in order to find if I have an edge from A to B, depending on the ordering of the edges, I might have to check 4 edges before I find it. And then between B and C, there's 2 edges coming out of B, so I might have to check 2 edges before I find the edge I care about. So it's O of N plus M because you could potentially have to check every single edge.
Okay, but let's take for instance.
That said, if your algorithm short circuits going from left to right, it could be just O M, because if you find a vertex by itself that doesn't have an edge, then you're done. So you could argue that it's O M, but just to be safe, like that's like if you have a lot of details in your head, like if you have a really, really strong understanding of graphs and runtimes, you can argue these things. But if you're just trying to get through an exam with limited time, you're going through the whole graph, just do O N plus M. It's easy, it's simple to remember.
Got you. Thank you.
Okay, I have a question on step 2, the check of TI and TI plus 1. Yeah. So I'm actually thinking of using the post array, or the post order array. Normally, when you have direct edges, they're supposed to be consecutive, right? But of course, if you have a forward edge, or you have a fork, they won't be consecutive. So there won't be a just plus 1 on top of I in terms of the post order numbers. I just want to check whether it's a general rule.
You shouldn't do that because you have no control, not really, of how the DFS is going to work itself out. So like if DFS decides to go down this long path of looking for the edge, and then it comes all the way back and presents its post number, you may not know that there's a edge in time. Like so like if I was to go to from A to B and B to C, right? C could potentially get its post number, then B gets its post number, and then A gets a post number. But I know there's an edge from A to C, right? So that's not really like a good way to tell if there's a that's like doing something really complicated to getting something really simple. You have an adjacency list. You know where the edges are. Don't mess with post order numbers if you're just checking for edges between the vertices.
Yeah, thank you. It's clear. Yeah.
Okay. Any other questions? Cool. All right, let's take a break. It's 3:57. Let's come back at like 4:02, 5-minute break. My loving wife, made me deviled eggs while I was doing this. So I'm going to use the restroom and eat these as my snack.
Thank you for your wife, and thank you.
Yep. What's been the worst part of this class so far?
Killing the programmer inside me every time answering the question.
Homework 3.
Which one was homework 3?
The coding one.
Oh. You know, we can't win with this class. So prior to this class, people hated the pseudocode and the recurrences of dynamic programming. People complain about it, how it's unfair, how it's like, why should I have to mess with this coding language that's like not real? Why do I have to learn recurrences? You know what I mean? This is, if this was code, I'd be able to check my answers and everything would be fine. I would get 100. So we're like, okay, well, we can turn dynamic programming into a coding exercise. We put a lot of effort into it. People will love us. We'll finally get to use code Python for dynamic programming. And now the other half of the students who would have preferred written pseudocode is all upset. I'm not saying that like we can't find like a balance, or we can't constantly improve on what we're doing to get to something that more students are happy with. But it is interesting to me that like no matter what choice we make, there is always some vocal group that hates the decisions that are made. I think I want to believe that like a majority of students are just okay with whichever delivery we choose, and that there is unfortunately just some students that for whatever reason the delivery method doesn't work for them, and they get upset about it. I'm not being like dismissive about it. I'm just saying that like it's really hard to find like the perfect way to deliver content to a class of this size. I think this semester started with 600. We've had semesters where we have 1,200, 1,400 students. We can't. It's impossible to please 1,400 students. I don't even think it's possible to please 100 students. So
because everyone learns differently.
Yeah, everybody learns differently. That's just the way it is. I mean, there are 49. There was 50 of you in this class, in this office hours. I appreciate every single one of you. Love hanging out with you guys. But for some other 500 students, these long office hours just doesn't work for them in terms of like gathering the information needed for the exam. And that's understandable. We try to give like alternative ways to sort of consume the material, but there's only so much we can do given how we have to scale. Your TAs are trying. Like I saw the post by Jamie. Hopefully you appreciate that Jamie has put a lot of effort and put a lot of thought behind these projects, and ways to improve them, and hopefully offer alternative points. They're not just like they're not presented on whim. There's a lot of hardworking TAs behind these decisions, and everybody's trying really hard. All right, let us move on.
We are trying our best too.
Yep, absolutely. Yeah. All right, chapter 4 is all about shortest paths. We have several problems to go over. I kind of want to skip maybe some of these, but we'll see how we go. Let's see, 4.3. Squares. All right. So remember how I said that we don't work with adjacency matrix in this class? And we still don't. We normally do not. This one's a little bit special because you actually solve it best using adjacency matrix. So adjacency matrices don't work very well because they kind of blow up your runtime. when you have a list of edges that you have to go over, such as with DFS or Dijkstra's or Prem's or Kurzweil's, any of the black box algorithms, having your runtime bounded by the number of edges means that just whether that edge is in the list or not means that you decide to continue or not on the algorithm. Using the adjacency matrix really blows that up. Just to see if the graph, to see where all the edges are, is an O of n squared operation, right? Like you don't know whether two vertices have an edge between each other unless you check it and then return it's true, right? So that's why we try not to work with adjacency matrix. That being said, if a problem requires you to sort of check every single pair of vertices, then it doesn't really matter whether you use adjacency matrix or list, because you're going to end up with an O of n squared runtime to start, and then you can only grow from there. So you're lower bounded by the check of every pair of vertices. Okay, so this is why this problem is solved this way. Okay, I think there's. All right, cool. So design and analyze an algorithm that takes as input an undirected graph and determines whether G contains a simple cycle, that is, a cycle which doesn't intersect itself of length 4. Its running time should be O of n cubed. You may assume that the input graph is represented either as an adjacency matrix or with adjacency list, whichever makes your algorithm simpler. So the fact that you could use an adjacency matrix is a big hint here, because it actually does help this the problem. If you were to use an adjacency list, you would basically convert that to an adjacency matrix in O of n squared and then continue on with this algorithm. But let's just assume that it's an adjacency matrix to begin with. And so let me illustrate what this thing is actually asking you to do. So if you have right, and this is your cycle of length 4. This is a 4-edge cycle, or 4-vertex cycle. Let me take that back. It is a 4 vertex. Let me just double check what this is. Doesn't intersect the self length. Okay, sorry, 4-edge cycle. So a length in this class, length and distance kind of used interchangeably, so be careful there. And then if you are asked about the distance of something, it is always assumed to be shortest distance of something unless otherwise specified. So the distance from point A to point B is typically assumed to be shortest distance. Okay, so the question is asking of length 4 cycles. So we are looking for any 4 vertices that are in this configuration. They basically make a square, and they have 4 edges between them that creates this cycle. Okay, so that's what the question is asking, whether this exists or not in our graph. All right, and so this is the approach we are going to take. All right, for all pairs of vertices U and V, check the row to see if they share at least 2 neighbors. If any such pair of vertices exists, return true. If not, return false. Correctness. This question is basically asking if 2 vertices shares 2 neighbors, right? So if at any point we have 2 vertices such that they share 2 neighbors, then they are a square, right? Makes sense? That's just what a square is. 2 vertices that share 2 neighbors. So if we look at it that way, then so by using an adjacency matrix, we can do this by checking by scanning 2 rows at a time for all pairs of vertices. we check n squared pairs, and it takes O of n to compare two rows in a matrix. Overall runtime O of n times O of n squared is O of n cubed. So what this looks like if we were to run the algorithm. It's basically we have a adjacency matrix, so our whether we have an edge here is whatever, right? It's like a Boolean matrix, Boolean array of whether you have an edge there or not. And then so the next vertex would be something like this, right? And then the next one is so forth and so forth. And so what we want to do is, let's say this is represented by this row and this is represented by this row. We want to start at two rows and see if there's some vertex along here where both of those rows have a 1 in it. Because if they do, it means that there's an edge to the same neighbor, and we need to get two of them. Okay, so if we say that this one is A, and then this one is C, when we scan both of these rows, we can see that we share one neighbor here, and we share one neighbor here. And by sharing those two neighbors, we have created a square. And if you want to scan every combination of two vertices, and so that takes O of n squared, and each scan of those two vertices is O of n, right? Because you're scanning two rows of size n, so that's O of 2n, which becomes O of n. And so O of n squared times O of n gives you O of n cubed, and that is your final runtime. Okay, does that make sense for everybody? Any questions? No? Cool. Okay. All right. Let's go to the next question, which is 4.8. So this is a good question. Yeah.
Sorry, I just had a not related to this question. I read somewhere that finding an n-side cycle is an NP-hard problem. Is that true?
The n-size cycle is an NP-hard problem. Yes, it is.
Mm-hmm. Okay.
I mean, NP-hard problems for like an n doesn't take away from the fact that for a small enough number or some special subset of that problem, it is polynomial, right? We say that SAT problems are NP complete, but the very specific subset of two SAT problems is a polynomial problem. So just because finding a cycle of size 3 or size 4 is polynomial doesn't mean that finding a n-size cycle itself is not NP-hard. Yeah. In fact, finding an n-size cycle is NP complete. It is NP hard, but it's also NP complete because you can verify it.
Okay.
Okay. Intersect itself. I think it's like a dumb way to say it, but like I think it just means that a 3 like you don't count this as a size 4 cycle. Even though like you could technically be like, I'm gonna go 1, 2, 3, 4, like that doesn't qualify as a four-sided size 4 cycle. Okay. Next problem is 4.8. I like 4.8 because this is the type of thing that like students ask about, and I never knew this was like an actual problem. In GPP, this is another problem that like question that students ask me, and I didn't know that this was like an actual GPP. All right. Professor F. Lake, aka Flake, suggests the following algorithm for finding the shortest path from node S to T in a directed graph with some negative edges. Add a large constant to each edge weight so that all the weights become positive. Then run Dijkstra's algorithm starting at node S and return the shortest path found to node T. Is this a valid method? Either prove that it works correctly or give a counterexample. So this doesn't work because if it does work, it would have been really simple for us to tell you, yeah, Dijkstra's works with negative edge weights, just make it positive and bam, there you go. So that should be like, you know, a clue of like you wouldn't need Bellman-Ford if Dijkstra's can just be manipulated to work this way, right? Like, why would you run a slow runtime like Bellman-Ford if Dijkstra's can just be undirected graph? I'm not actually sure why this question specifically asked for directed graphs. Is simply no matter what. And I'll give an example as an undirected graph because I think it's kind of like easier to look at. So it says to come up with a counter example. And so that's what I do. All right, so the idea is that like if we had a bunch of negative weights, what we can do is that, okay, well, let's just take whatever would make this positive and add it to all the other edge weights, and bam, my entire graph is positive, right? And so if this was our initial graph of 1, 2, 3, 4 nodes, and then we do -1s all the way here, -2, right? Our shortest path from 1 to 4 is from 1 to 2 to 3 to 4. Now you might ask, why is that the shortest path? Remember, your shortest path on a weighted graph is your lowest possible number. And while this takes 3 edges and gets me -3, if I was to go from 1 to 4 directly over one single edge, that only gets me a -2, right? So -3 is lower than -2. So that's my shortest path. Now, what we want to do is like, okay, well, let's make this all positive. So if we add 3 to all edges in order to make them all positive, we get 1, 2, 2, 4, right? Now, if we do it that way, now the shortest path, if I was to go 1 to 2 to 3 to 4, would be 6. But if I go directly from 1 to 4, it would be 1. So it changes what my shortest path would be really versus what my shortest path is with Dijkstra's. First of all, I understand that this is a negative cycle, right? But you're let's like forget about that negative cycle begin with, because, well, first of all, that's one of the reasons this doesn't work, is because this would create a negative cycle. This would not create a cycle, and so you wouldn't be able to detect that if that's what you were trying to do. But let's say it didn't have a negative cycle, then if you were to terminate, this would be -3, this would be -2, and then this is now 6 versus this 1, which doesn't work. Right. And then so one of the reasons is that the magnitude of which you have adjusted your path, the longer a shortest path is, adding the same number to every single edge has a bigger impact than adding a single number to a path with a single edge, right? It's scaled more, right? Like if your shortest path is 5 edges, and you add 100, you've just scaled that path weight by 500. If your shortest path is, if your second shortest path is of edge weight 2, and you add 100, then you've scaled that path by 200, right? So you could tip the scales of what the shortest path would have been and with or without the adjustment. So that's why this kind of adjustment just doesn't work. Okay. Any questions about this problem? Cool. This kind of thing, this kind of like change does work for MSTs, because MSTs is concerned about each individual edge at a time. So each individual edge is decided to be included or not based on whether that edge is optimal or not. So you can do this with MSTs. You cannot do this with Dijkstra's because Dijkstra's decides on the path based on the combination of edges. And so your impact on your path is multiplied by the number of edges in that shortest path rather than each individual edge in a comparison. So it does not work like that. Okay, moving on. Next problem is 4.11. Yeah, I'll go for 4.11. That's fast. Yeah, I'm gonna paste the whole thing because 4.11 for Warsaw is technically covered as a DP. And in previous semesters, I think it's because due to the adjustment of the schedule for summer. In previous semesters, 4.11 is actually assigned during the dynamic programming topic. All right, shortest directed cycle. Given algorithm that takes as input directed graph with positive edge weights and return the length of the shortest cycle in the graph. If the graph is acidic, it should say so. Your algorithm should take at most O of V cubed. So what we're going to do is we're going to run Floyd-Warshall on G and get back a distance matrix. So the distance matrix tells us what the shortest path between any two vertices are. For all pairs of vertices, check that distance from U to V plus the distance from V to U, and return the smallest sum among all these vertices. So a cycle from U to V is defined as the distance from U to V and from the distance back from V to U, right? So that's our cycle, the shortest cycle. And if the smallest sum is infinite, which means that we could not find any cycles, then the graph is considered acidic. So the reason why this works is because Floyd-Warshall gets us the shortest path of all pairs of vertices. Since the graph is directed, a shortest cycle between any two vertices is the shortest path from U to V and then from V to U. The shortest cycle in G must be between two vertices. So checking all pairs of vertices will find the shortest cycle in G. Floyd-Warshall is O of n cubed, and checking the distance between all vertices is O of n squared, and therefore you end up with a O of n cubed runtime. Any questions?
Are you taking any vertices?
Sorry, someone needs to go first.
U and V, is just any two vertices or all vertices in the graph?
All pairs of vertices.
All pairs of vertices, okay.
Yeah.
Would this be equivalent to running Dijkstra and then for each pair find the distances that Dijkstra gives you from U to V and then V to U and try to minimize that?
You would have to run Dijkstra's on every vertex, right?
I'm assuming that I have a adjacency matrix. Then for each row of the matrix, I could run Dijkstra to get the shortest distance from that vertex to every other vertex.
Mm-hmm.
And then I can calculate the same formula that you have here and find the minimum of it.
Okay, let me see. So Dijkstra's runtime is that can work. I just want to make sure that that's actually optimal. Okay, textbooks. Okay, so if our Dijkstra runtime is that, right? And then you want to run this n times, right? So what does that give us? Because you have to run it from every vertex so that it gets the shortest path through every other vertex. So that would be n squared plus n plus times. So this n multiplies with the n gets n squared and m, and then we further multiply that out with n log n. And since m is capped by n squared, that dominates that. I don't think this is good. I think what you end up doing. Oh, why can't I? I think you end up multiplying one additional. So like this is gonna get dominated by the n times m. This is gonna be O of n squared, n cubed, and then it's gonna be O of n cubed further multiplied by. Oh wait, no, I don't multiply that. Hold on. Yeah, because it's multiple. Okay. So log n. So it'd be like O of n cubed times log n, I think. Which I don't think it's faster. I think you get that additional log n in there.
So this would be less efficient than ON3.
Emily's really good at these. That's why I'm going to ask Emily, but I don't know if she's here anymore. Emily's not here. Okay, I don't think this is fast enough. I think this is going to end up with O of n cubed times O of log n at the worst case, which is slower than O of n cubed.
Okay, thank you.
I had a minor question here. So instead of checking all of the pairs in the table, could we not just check the diagonal of the table, since that'll check for like whatever the shortest cycle, like a given, like if you're looking along, like, you know, like, what am I trying to say here? It'll give like the shortest cycle which contains whatever vertex you're looking at in the diagonal.
Yeah. So I looked online on how people code up Floyd Warshall, and I avoided that solution. I actually think that in this class we could possibly allow for that solution, but in a lot of implementations of Floyd Warshall, when a vertex is considered against itself, it's set to 0 as the distance. So that entire diagonal is set to 0 in most in most implementations. In this class, when I was looking at the pseudocode in the book, it can be argued that that would be started off as infinite, and then it would be compared against paths. And then when you check to see each edge, because technically a vertex doesn't have an edge to itself in the adjacency list, it would not get set to 0. But I was uncomfortable of giving you that definitive answer, like, oh, you could just check the diagonal. But I think this is a more clear cut, a clear solution anyways, because you can easily visualize why this works. But if you were to have presented that as your solution, I think it could be argued that you could just check the diagonal.
Okay, yeah, thanks. Yeah, I was conflicted on that because it seems like the way DPV and the lectures do it, yeah, on the diagonal is different from pretty much everything else I find.
Yeah.
So, okay,
Yeah.
thanks.
Yep. All right, any other questions? All right, moving on to the next problem. For shortest undirected cycle over E. So this is 4.12. All right. Given all of V squared or all of N squared algorithm for the following task, an undirected graph G, edge lengths L, which are positive, and edge E, output the length of the shortest cycle containing edge E. Okay. All right. So my approach is to remove the edge. Remember, this is one of those key things to consider doing is to just remove the edge that's special when asked about that edge. Not that every single problem like this is solved the same way, but it's certainly a strategy and something you should consider when presented with a problem. Run dexterous from U on this updated graph, and then return distance of V plus LE. Okay. Because we have to include our edge EV in our cycle. The way to minimize the rest of the cycle is to find the shortest path that completes it, right? So if we remove that edge, remember this, any given cycle has at least two unique paths from any two vertices within that cycle. So if we remove that edge, we should be able to find another path from U to V within our graph. And so by removing it, we remove part of the cycle that E would have created. We then run Dijkstra's from U to get the shortest path from U to V without the use of that edge. And then our shortest cycle is in the shortest path from U to V without E plus E to complete the cycle. Hope that all makes sense. This actually ends up being bounded by the runtime of Dijkstra's. I don't actually know why. This is confusing to me. I don't know why it asks for a O(n) squared algorithm, but we can certainly force it. We can say, while we normally use the binary heap version of Dijkstra's in this class, we can use the array version of Dijkstra's, which is O(n) squared, and that gives us the exact runtime that it's asking for. If this was asked for by this class as like an actual problem, we wouldn't give you this runtime and tell you to make it worse than it could be. You wouldn't need to give a O(n) squared algorithm. I like to joke about these type of things, like if I'm given a runtime that's worse than my best than the optimal solution, I would just mess around. Like instead of using this array version, which I think this problem is clearly trying to push me towards, I'd be like, for every pair of vertices, list something I am thankful for, and that would get me that extra random O(n) squared runtime that has nothing to do with the problem, and then I would just give my original algorithm. Yeah. All right. Anybody have questions about this solution?
Didn't we discuss that removing an edge is big O of M previously?
Removing edges. Yeah, it would be O of N or O of M. Could also be O of N plus M.
Did you remove the engine? Did you remove the edge by deleting it from the linked list?
Yeah.
I have a question.
Hold on. This should be. I would make this O of M. You're correct. That's a little bit more clear. Okay. Let me update it in my notes so I don't make this mistake again. Make this so O N M to remove E. All right. What's your question?
My question is like this one, because you see they need us to specify that we need array instead of a binary heap. So my question is, when we write the algorithm, do we need to be more specific about our implementation? Let me give you another example. Say I want to delete a node from a graph. Then actually I can do it in constant time because I can just use another array, Boolean array, to keep whether each node it remains in the graph or not. So that only takes constant time. But if you think in another way, if I reconstruct the adjacency list, maybe it takes longer time. So, so do we need to write down those details? Actually, I have a array keep track of whether each node is in the graph or not, something like that.
I would say that if you use what the class has presented to you as the runtime, you don't have to like do anything special about it. Like we have said that removing a vertex is O of 1. We have said that removing an edge is O of M. We have said that Dijkstra's is O of N plus N log N. Like these are sort of like accepted runtimes that we've presented in the class, both in the mostly in the lectures and in our post. So you can just do that. If you think that there's a very highly special way you need to remove a vertex or edge or run Dijkstra's in order to do something special about your runtime, you would have to give us the details. I would say that most of these have like a known runtime that you can just state and you would be fine.
Okay, thank you.
And again, this is like the only reason I gave the whole array version is so that because if this was said, if this said just this part and not this top part, I wouldn't have done that. Or if it said, your runtime must be O of N squared, I'd be like, okay, well, I beat O of N squared, I'm done. But because it says give a O of N squared algorithm for completion's sake, I decided to do this. But like I said, I would mess around. I would be like, do something that has nothing to do with the problem just to take up the time of O of N squared so that I can reach that target runtime, because there's actually no need for this. All right, any other questions? All right, if not, let us move on to the next problem, which is 4.13, cities and highways. Did you get a solution to 4.13?
Checking 1 second. I think we got one for 4.14. Yeah, we got one for 4.14. We didn't get one for 4.13. Thank you.
All right, so I will present to you a solution for 4.13. Now, let me post the question first, and I will.
Sorry, I do have a bit of a break question, I guess. A little irrelevant question. Are you using Microsoft Word to maintain these notes?
I'm using Google Docs.
Nice. Right. Yeah, you were right, Tim. Solid.
I don't want to make anybody angry, but I am not a huge fan of Microsoft Office type products. I don't. It could be that I'm biased and I haven't used them in forever, and I've been sort of forced to in this role as a TA because Georgia Tech uses a lot of Microsoft products, so I'm just not used to them. So they just feel really clunky and awkward to me. Probably mostly my fault, but yeah, I don't like using it. I mean, I'm using Whiteboard because because I have to. Yeah. All right. This 4.3. Okay, so 4.3 asks, you are given a set of cities along with a pattern of highways between them in the form of an undirected graph. Each stretch of highway connects two of the cities, and you know its length in miles. You want to get from city S to city T. There's one problem. Your car can only hold enough gas to cover L miles. There are gas stations in each city, but not between cities. Therefore, you only take a route of every one of its edges has length LE less than equal to L. Given the limitation of your car's fuel capacity, show how to determine linear time whether there is a feasible route for S to T. You are now planning to buy a new car. You want to know the minimum fuel tank capacity that is needed to travel from S to T. Give a O of n plus m log n algorithm to determine this. So you'll notice here I have on this one says Dijkstra with mod. When this problem was presented to me as a student, it was as a practice problem, and because it is a practice problem, DPV is outside of what this class can control. It very clearly wants you to modify Dijkstra's, right? Like it gives you Dijkstra's runtime, and then it says use, find a solution with this. And so it's very clear that you're supposed to mess with the Dijkstra's path calculation. So I'm going to give you a solution that sticks with what DPV wants you to do. That being said, our class does not allow for the modification of black boxes. So after that, I will present to you a acceptable solution that we would allow that doesn't require the modification of a black box. I think both solutions are interesting to see because they're actually pretty different. And then you can let me know which one you prefer. All right. So keeping with the, we are going to modify our black box algorithms. Part A, I am going to modify the explore algorithm. Now, again, do not do this on the exam. You will lose points. But since this is what the book wanted us to do, let's start with that. So in the explore for loop that goes over each edge, we add an additional check that if our edge is greater than the capacity of our tank, we just don't process it. We just skip it. So any edge when exploring is beyond our tank capacity, then that edge cannot be explored because we cannot go down that road because our tank capacity won't allow it. So we run this modified explore on G as in get back visited. So it visited our destination city T is false, then it's infeasible for us to get there. If it is true, which means that having avoided all the highways that we aren't allowed to take without tank capacity, if we can still reach T, then it is feasible for us to go from S to T. And the correctness is explore normally find a path from S to OV if it exists. In our modification to explore, we're explicitly avoiding any edge that has a length of greater than L, knowing we cannot take it. Results in explore find a path from S to T only if it can find a path over edges that our tank capacity can handle. And our modification is O of 1, and therefore it is the runtime of explore, which is O of n plus m, and this is considered linear. And so that's what happens if you had to modify it. Now, if you didn't have to modify it, it's actually just as good and probably, to me, a better solution. You basically just modify your input to remove all of those highways that you can't take anyways. So we create a G prime such that G is without E star, where E star is all edges E such that its length is greater than our capacity. So that is we remove from G all edges that have a length greater than L. and then we run the explore algorithm again, and we check visited, and if it's false, then you can't reach it. If yes, then it is feasible. And this works because we first remove all highways edges that our car cannot travel over given our tank capacity. Once those edges are removed, then all remaining edges can be traveled on without tank capacity. So an explorer from S will give us all the cities that we can reach, and if we can reach T, then it is a city that we can reach. And that's same runtime, right? The exception being that we have this remove edges that are greater than our capacity, which takes O of n plus m, because you have to check every single edge. And then running explore is once again O of n plus m, and this is considered linear. Okay. Any questions about these two approaches, why they work, and why the one on the right is allowed and the one on the left is not?
So my question on the approach on the graph algorithm design is we are allowed to modify the input, meaning that map the problem statement to a graph problem, and we move any obstacle from the graph problem that we represented, and then apply the known black box algorithm to it, and then manipulate the output. That should be our approach, right?
Yes.
Thank you.
All right. So now the more interesting problem, which is part B, you're now planning to buy a new car, and you want to know the minimum fuel tank capacity that is needed to travel from S to T, given O of n plus m log n algorithm to determine this. And so this is asking us to modify Dijkstra's. And so if we wanted to modify Dijkstra's, our solution is going to look like this. All right. So rather than set distance v equals minimum of distance u plus the length of uv for all UV edges. So this is the Dijkstra, this is the part of Dijkstra's algorithm that's in the book, right? You basically get the distance to some vertex, and then you add the length of the edge to V, and you want to find some minimum distance to V. You find from the previous all the other minimum distances, you add an edge to it, or add more edges to it, and you find this minimum distance, right? This is Dijkstra's. You should know this. What we're going to do is going to modify this check. So what we're going to do is we're going to find the maximum of this, and we're going to get the minimum of it. So what we want to do is we're going to look for what is the edge, the maximum edge for us to take a path. So if I'm taking a path, because I don't care about minimum distances anymore, right? I care about the what's the limitation is. Like if I'm going from A to B to C to D, like let's say this is my path, right? I no longer care that this distance is 9. What I care about is that I need to be able to travel over this road. So all I care about is what the maximum edge across this path is. Now, once I know what the maximum edge across this path is, I want to get the minimal about that. I want to get it so that I can travel from A to D over some minimal maximum edge. Right, and that's what this modification does. And so that is, rather than seek a minimum path from S to T, we seek a path using the minimum maximum edge needed to get from S to T. this upside down for all, for any, yeah, for all, for any. I think, yeah. So I want to find this thing, and I want to check all edges in E. This was when I was taking the class, and I thought like, we wanted to go like, super math notations. Turns out we don't. I should probably rewrite some of these because those are kind of like a pain in the butt. Yeah. Okay. So our correctness is that the original Dijkstra algorithm gives us the shortest path from S to T by seeking a minimum path via sum U plus LUV. This tracks the shortest path from S to all V. Our modification instead seeks a minimum maximum edge from S to all V. We do this by setting distance V to the minimize maximum distance of U, L, V, UV. And the inner maximum, make sure we are tracking the maximum edge we must take to get from some U to V. We then minimize this so that we can get from S to V over the smallest possible maximum edge. Modification is all one, and therefore it's the same runtime as Dijkstra's of n plus m log n. Okay, does this make sense? Like instead of finding the shortest path, we're finding the minimum maximum edge. Maximum edge being defined by the largest edge across a path.
Couldn't we instead find the shortest path and find the maximum weight edge on that?
No, because what might happen, okay. So our shortest path from A to B is 10, right? Because that's just 10. And if we go from A to C to D to E to F to B, that gives us 5, 10, 14, 17, right? This D is equal to 17, right? So obviously we'd rather take the 10. But what happens if I told you, well, your capacity is only 6? Okay, if my L is equal to 6. The top path from A to B, even though it's the shortest distance, isn't available to us. We can't travel 10 miles on a capacity that only gives us 6. So our best path, or our only path in this case, is from A to C, which takes 2, and then we can refill. C to D, which takes 3, then we can refill. D to E is 5, and so forth, and 4 and 3. We can take the bottom path by refilling each time. We can't take the shortest path. We're not allowed to. So when we consider this, right, what we want is to get the path with the smallest maximum edge. Does that make sense?
Yeah, it does. I mean, we're not allowed to modify the black box, but if we could, we could also run Dijkstra multiple times if it doesn't satisfy.
You don't want to run Dijkstra's multiple times, because then your runtime is all of n times the run of time of Dijkstra's, and that's suboptimal.
Okay. Thanks.
Okay. All right. All right. Can I do this? If I grab all this. Why did that? What? Oh my gosh! What just happened? They just deleted everything. What? What did I just do? You just deleted everything. Oh, coming back. Oh, coming back. Okay. Okay. Whew. What I wanted to do was grab all this and move it. Cool. Hey, if you have a recommendation for a better app than Whiteboard, go ahead and let me know. What I need is something that I can draw on my tablet and share and present it with the class in a web browser. Any app that does that kind of thing really well would be cool. All right. So let me paste my other solution to this problem. I don't use an iPad because I don't actually have like an Apple account or that I use. I only have a Google account. I don't really have like a thing against iPads. Is that everything else I own is Android, so it's like it would be weird to have one thing that's not in my ecosystem. All right. So I'm going to turn this into an MST problem. And what's interesting is that we can solve this slightly faster than the Dijkstra approach. And okay. Okay. All right, let's go with it. So first, I'm going to say, assuming S can reach T, and we can run Explorer to confirm. And the reason I say this is because even though I'm going to turn this to an MST problem, it wasn't presented as an MST problem. And so because it wasn't presented as an MST problem, I can't assume that my graph is connected. I can't assume that S can reach T. And over here, when I run Dijkstra's, because Dijkstra's handles if S can't reach T, I don't have to care about it. But over here, because I'm turning it into MST, I have to make sure that S can reach T first. Once we do that, we are going to take the graph, and we're going to run Kruskal's to get an algorithm to get a MST of G. Now we're going to run a Explorer on M, which is the MST from S, and we're going to get this previous array. Okay. And then we're going to set max edge to 0, set U to T, and then while U is not S, set the max edge to the max edge plus this edge I'm going to, and then update U to previous U, return. So that's all like super complicated. I'm going to type this out in a better way, actually. I think, again, this is one of those situations where like when I first took it as a student, I thought I had to come up with like this really descriptive way to say this. I'm just going to say, take the using all right, let's do this. We're just going to take this updated one, and we're going to put right over L step 3 and 4. Okay, so now it's much easier. We're just going to take the previous array. We're going to take the path from S to T and return the longest edge. That's what we care about. We want to know what the longest edge between our path of S to T is, and that is going to be our capacity that we need. And the reason this works is because we first confirmed that S can reach T with a run explorer. We don't care about the shortest path with the algorithm. We then create an MST which is guaranteed to collect all nodes using the minimum edges. Since our tank capacity is limited to the maximum edge we must take to get from S to T, going over the minimum edges will minimize our tank capacity. We then run explore from S over the MST, which can only have one valid path since it is an MST. This valid path can be traversed to find the maximum edge along the path. This maximum edge determines our tank capacity needed to get from S to T. So if you think about it as an MST problem, first of all, I can only have one path from S to T, right? Because I cannot have a cycle in my MST. So now I know that there's only one path. So if I run and explore from S, I will get my single path to T. Then from S to T, I know that the MST algorithm has picked all the smallest possible edges to get from S to T, right? It's going to use the minimum edges in my tree. And because those edges are minimal, whatever that edge, that's the largest edge, is going to be the tank capacity that I need to get from S to T. Okay? So the runtimes is running explore, running Kruskal's, run explore again, and then traverse preef to find the maximum edge, and you get a overall runtime of Kruskal's, which is O of M log n, which actually beats the Dijkstra's approach. Okay, and this is how you find the solution without having to do a modification. Any questions on this approach?
All
right.
One.
Yep.
I do have one.
Yep.
So
Go
there's
ahead.
there's other nodes in the graph, and so what if we find an MST which gives us the optimal minimum tree for the whole graph? How do we know that that's going to be the same MST usable for going from S to T?
Sorry, say that again.